Good morning, good afternoon, and good evening to every one of you joining us from around the world. We warmly welcome you to the information session on ASIC, FPGA, and short course on SystemVerilog for Design and Simulation, organized by the Department of Electronic and Telecommunication Engineering, University of Moratuwa, Sri Lanka, together with Synopsys and SkillServe. We all use computers every day to make our lives better and easier. In fact, computers have become an essential part of our lives. All the wonders of a computer are made possible by its CPU, its brain. But have you ever imagined how a CPU is designed? How fascinating would it be to design your own CPU? I know at first it might seem daunting, but actually it is only so until you learn how to do it. And you have chosen well and come to the right place to kickstart your journey in processor design. This event will be the inaugural session of the short course on SystemVerilog for Design and Simulation and an information session on ASIC FPGA. As you can see on our agenda for today, we have invited prestigious guest speakers and a panel of lecturers to give you a great exposure into the world of ASIC, FPGA, and processor design. So, without further ado, let me introduce Dr. Ranga Rodrigo, the head of the Department of Electronic and Telecommunication Engineering at University of Moratuwa. He is also a supervisor of the SystemVerilog for Design and Simulation short course. He is a distinguished alumnus of our very own department, graduating with his bachelor's degree in 2001. He obtained his PhD in computer vision from the University of Western Canada in 2008. Sir, I cordially invite you to address the audience.
Thank you, Chatuni, for the introduction. I warmly welcome each one of you who is joining from Sri Lanka and different countries for this exciting session of SystemVerilog for ASIC FPGA Design and Simulation. So as Chatuni mentioned, when we see an IC or a processor in a computer, we get so excited. How does this work and how can we contribute in making such a complicated system by ourselves? So perhaps if you are not thinking like me, who is not very well versed in this area of SystemVerilog, it may not be a daunting task. So through this course, we want to demystify some of these ideas. And if you are already experienced in this area, you will gain a lot in how we think in processor design using SystemVerilog. So we are very excited to have Dr. Theodore and Farazy also joining us today so that we can give an overview of this course and what matters in SystemVerilog for processor design. So we have gathered a number of lecturers from different parts of the world who have mostly been our alumni, and they will, with a lot of vigor and excitement, share their knowledge with you. So the Department of Electronic and Telecommunication Engineering is one of the departments in the engineering faculty of University of Moratuwa, Sri Lanka. It is one of the best universities in Sri Lanka for technical education. So we have been doing exciting things over the past 50 or so years. There has been an interest to share our knowledge as a university. Of course, this is in addition to the preserving and creation of knowledge through our research. Through the history of our department, we have been able to do exciting things in winning competitions and so on. So we want to share those expertise with you also through this course. Now, to show you a few more achievements of our students, actually these are undergraduates. Actually, Chatuni also spoke to you a few minutes ago. So she and the teammates won Innovative FPGA Grand Final Silver Award. And actually before that, they won the Asia Pacific and Japan Gold Award for this. So like that, there have been great achievements in this area. For example, one of the students last year, just after undergraduate studies, joined Meta. So you can see a picture with Jan Likun there. And some of them joined Harvard to carry on with their research work that they did as undergrads at the department. And we have been able to reach top conferences and journals through publications like information theory and so on. So there's a lot of expertise. And we want to share that knowledge with those who are like-minded, like you. So that's why we are very excited that many of you have joined us. It's night for us now in Sri Lanka tonight. So thank you for joining. And thank you all the lecturers for enthusiastically contributing to this program. I usually designing a program to span 8 weeks and to deliver the knowledge on SystemVerilog and take the project-based learning approach was not an easy task because we had to think about the timeline as well as to give a sensation of accomplishment, a true sensation to the participants. So I think the curriculum designers led by Dr. Subodha Charles and others have been successful in that regard. So I wish you a very exciting journey throughout these 8 weeks. Please do continue to participate in the program. Once again, thanking everyone who's joining and the keynote speakers, Theodore and Farazy. I wish you all the very best. Thank you.
Thank you very much, Dr. Ranga Rodrigo, for those insightful thoughts, especially about how our department contributes to the world of technology. Moving on, now we are coming up to a very exciting point in our agenda, where Mr. Kaveesha Yalegama from final year at ENTC demystifies an electronic chip and walk you through his journey from Arduino to Apple M1. Mr. Kaveesha, the stage is yours.
Thank you, Chatuni. Yeah. So let's start with something a bit familiar, software programming. This example is from embedded environment. For software programming, you start with the algorithm. Then you convert that algorithm into a program using any number of programming languages, C or C++. Then you compile it and assemble it into machine code, which has simple instructions that the CPU can understand and execute. And then finally, this machine code will be uploaded into a CPU, which in this case is the CPU in the Arduino board, and then into a final product. This product is from this is from a previous course. Okay, so note here that we are creating a machine code from software programming. We are creating a machine code which is going to be run on a hardware circuit, the CPU. So in this course, we are focusing on the CPU, creating the CPU part. Okay, now let's look at the CPU. The CPU on the Arduino board is the Atmega CPU. Here you see the external view of it. You have pins coming out of it for power and inputs and output for the CPU. Okay. Now let's go in a bit deeper. Let's go inside the IC. Here you can see after the topmost thing removed, you see a small black square in the middle. So that's the actual CPU circuit that does the work, that executes your program. It's not like it has several layers, so even though you can't see it directly, there's more than one layer here, and you can actually remove those layers and go look inside a bit more. So you can see, you can look at the transistors and everything by removing the layers. For more information on delayering, you can click through these links. Okay, I said it has a lot of layers, and these layers are on top of silicon. Silicon is used to create the transistor that does the actual computation. So it's not just enough to create the transistor itself, you have to connect them. And connecting parts is where the metal layers come into play. So you have several metal layers to connect each transistor together to build your circuit. So it's very complex. Now let's appreciate the scale of digital design. Here in this video, we continuously zoom into a digital chip in a digital camera. I see, even though the IC package is much larger than the actual CPU itself, but once you zoom in a bit more, you can see amount of detail that's there, right? The more you zoom in, the more details you see. So this is like a lot of components there, a lot of complexity you have to handle, a lot of components. So we need a SystemVerilog and the abstraction that the ASIC design flow allows us to handle this complexity. We will learn the ASIC design flow throughout this course to handle this complexity. As you can see, the more you zoom in, the more details are there. And at this level, you can actually separate out the separate things in the IC. But the size is at 1 micron. That's one millionth of a meter. So that's the scale that digital design engineers work at. So yeah. So, but still, even though this is like 1 micron thick, we still need to go smaller and smaller to create better and better chips. So that's where like complications start to arrive. Okay, let's look into a machinery of a CPU. So this is a very popular CPU called the 6502. We have few examples here: Apple 1, Apple 2, Atari, and Atari console, and the Nintendo consoles. But it's very popular, and it's used in a lot of machines. The good thing about this CPU, the good thing about it being very popular, is that people play around with it, and they want to, like, they have worked around with it, and they have several things. So this is one such thing. So in this website, the link is there on the slide. This website has simulated what it's like to run a program on the 6502 CPU. So on the right hand side, we have the actual programming machine code. So this is the output of compiling and assembling your program, which is then run on the hardware circuit. Like I said before, we are focused on creating the CPU, which is on the left hand side. I encourage you to go through the go through this website a bit more and try play around with it. Okay. Now let's come into what's happening in the present. I'm pretty sure you guys have heard of the Apple Silicon. Even though it's one of the most popular news in tech right now, but there's more than Apple that's trying to innovate and bring new technology and enable new computational power to do new things, right? So there's a lot of things happening. Like we are like I said before, we are trying to go smaller and smaller. It comes with new problems that we have to solve. But once we solve those problems, we get more computational power. So the space is very interesting. Even for me personally, RISC-V, I have to shout it out. RISC-V has enabled a lot of people to get into computer architecture and design. Throughout this course, you will see a RISC architecture and a RISC CPU. And it's a very interesting space at the moment. And I'm really interested in seeing what the future holds in this area. Over to you, Chapin.
Thank you very much, Mr. Kaveesha, for delivering such a fascinating review about the journey of the electronic chip. Next up, we have our first keynote speaker for today, Dr. Theodore Omtzigt, the president and founder of Stillwater Supercomputing and the chief technology officer of Lemoria Labs, USA. He is a proud graduate of the Delft University of Technology, graduating with a bachelor's degree in electrical engineering. He obtained his PhD from the Yale University in computer engineering in 1992. He has worked as a research assistant at the Yale University during his PhD. Dr. Theo joined the Intel Corporation the same year and worked as a senior computer architect. He later worked as He later worked at 3DFX Interactive as a principal engineer and at NVIDIA as a system architect. In 2006, he founded Stillwater Supercomputing, a company that develops high productive platforms for real-time intelligence. He still serves as the president of Stillwater Computing to date. Dr. Theo became the Chief Technology Officer of Medicare Pathfinder in 2017 and the Chief Technology Officer of Lemurian Labs that develops custom silicon chips for visuomotor applications in May 2002. He has years of experience in high-performance computing, cloud computing, and software development. Dr. Theodore, we are extremely grateful to have you with us today. I warmly invite you to address the gathering.
All right, let's see. That was an awesome introduction. So thank you for that. Can you guys hear me?
Yes, sir,
Yes,
we can.
All right. Let me switch it up a little bit and give you a sense of a career in microelectronics and hardware design. I was asked by Abba and the team to give you sort of a lowdown of the things that I've been working on through the years and to identify sort of the exciting aspects of being a hardware designer. Now, as you saw by the introduction, I've been in this space quite a bit, and effectively getting on to 40 years, and I am still incredibly excited to see and work on ASIC designs and computer architectures. So what I wanted to do was give you an overview of the years and the products that I worked as a young engineer, and then sort of transition into a discussion of what is sort of happening in today's industry and what the future holds. So I started as a young engineer coming out of grad school at Intel. I had started as a solid-state physicist actually in undergrad, but became interested in silicon compilation and EDA tools because when I was going through undergrad, this whole VLSI industry started to sort of come of age, and all of the problems of dealing with that complexity that the previous speaker identified, it was clear that you needed automation to be able to deal with that. So I became interested in EDA tools. Then after graduation, went on to do research. And as a matter of fact, in the late 80s, I was interested in the synthesis problem. This was before logic synthesis, and I actually worked on work that today would label itself as high-level synthesis. I was actually working on systems that would take algorithms and synthesize them across multiple chips, even. So that work was really done for very high performance systems, typically real-time systems. And these systems were really frequently targeting either embedded systems or supercomputers. So after grad school, I really wanted to go to the supercomputing industry. But when I came out of grad school, we went through an economic downturn and those companies all went bankrupt. So I ended up at Intel, and this was serendipitous because this was right at the time that Intel started its growth. So when I joined Intel, it was a $4 billion business. When I left Intel 6 years later, it was a $24 billion business. And in those early days, I was basically studying and designing caches and memory controllers for processors. So in those days, a processor had an option to have an external cache, because at the time they couldn't really integrate a level 2 cache on the die yet. So you had a very complicated problem where the CPU, which is running at very high frequency, had to connect to an external secondary chip on its caches. And then that cache, when it would miss, it would have to fetch to memory. And those systems were had to be built in a very cost-effective way. So the first couple of years I was working on these cache and memory controllers, and particularly interested in modeling the performance that you would have for different caches and different memory controllers. So in that, I'm proud to say that I worked on the first PCI that was a peripheral extension bus that was taking over from the previous bus called the ISA bus. And the first chipsets that delivered that to the industry were the chipsets that I worked on, the Saturn, Mercury, Neptune, and Triton chipsets. Then we sort of started to look at graphics and integrating graphics. And at that time, the mid-90s, you couldn't really integrate a full graphics controller on the same chip as a chipset. So there was a stopgap measure design called the Accelerated Graphics Port, HGP. And HGP was basically, for about 8 years, the vehicle with which high-performance graphics was interconnected to these chipsets. So I was part of that design team that built the first HGP protocols and HGP chipsets, and then also the first that connected that to a graphics controller. But really, the thing that I'm most proud of in that period is the work I did on Intel's first diagnostics platform processor. And what this was a real-time diagnostics processor that was keeping track of transactions and latencies and throughputs of the transactions that are taking place within these chips. And the reason for that was, by measuring them, we could actually see how well we did with our modeling and make certain that if we had any blind spots, that we could fix those. That was stuff that at that point had only been done at the supercomputers and the mainframes of the day, but in the full 40 LX and BX chipsets, I was the one that put that in PC pieces, and I'm still very proud of that work. Before I sort of go, at that time there was also a processor change happening. So we had 46 to Pentium Pro, and these were dramatically different architecture. So 486 was really a straightforward design, in the sense that it had multiple clocks for an instruction. But as this period is sort of a period of computer architecture where we're trying to improve or increase the concurrency of these systems, there was a lot of work being done in building what they call superscalar, which were basically machines that were processing multiple instructions concurrently. And the Pentium was the first one, and the Pentium Pro was really, at that point, the most advanced microprocessor that the industry had seen. It had out of order execution. It had a novel architecture that would do an hardware compiler effectively to translate x86 instructions, which are very complex, into faster, more predictable micro instructions that were the execution engine of the core itself. Now, there's one thing that I want to call out here, and that is, it is very common in very large organizations that there are multiple projects in flight. And the reason for that, it takes 2 or 3 years to build a complex chip like a fast microprocessor, but the market can change much more quickly. So what people sort of recognize is that if it takes you 3 years to design a processor and the market suddenly midway turns to a different direction, you would basically risk the company and its future. So what these large companies do is they tend to have, so say that we have a 3-year design cycle, but it is possible that the market changes in a 6-month period, then you have 6 concurrent projects that at any point in time could be dropped into that changing market. So it is very common in these environments that you have multiple projects, and most of the projects never make it to production for the simple reason that the market has selected a project that you are not working on. So that was the case in these processors that I was working on at Intel in the mid-90s. One in particular was called the P55C. And remember, in those days, a PC was like $6,000. So the market really didn't want or didn't like the idea that every 2 or 3 years you would have to pay another $6,000 to buy a new PC. So the market asked for an upgrade path, and these were called the overdrive processors. And these were basically the next generation processors that Intel would make, but we would stick them in the basic package and protocols of the previous generation. So we would take a Pentium and stick it in a 486 environment, and we were working with P55C to take the Pentium Pro and stick it in a Pentium package. Well, at the time, when the PC market was growing very rapidly and AMD was competing with Intel very, very effectively with a good Pentium design, the P55C, which was an overdrive processor, was killed because Intel wanted, from a competitor's point of view, move the industry to a bus that they would control. So I was unfortunate in the sense that I was working on an overdrive processor that never saw the light of day. But it's something that you need to keep in mind, is that this is not the end of the world. These things happen, and it's just a fact of life in this very long and complex product development cycle of electronic design devices. So after Intel, the last project I was doing at Intel were integrated graphics and integrated graphics chipsets. And I really got interested in this whole world around graphics and graphics processors. They were fantastic devices, and you could not use all the transistors that these chip technologies had at the time. You could use multiple devices in order to build higher and higher performance GPUs. Or at the time, they were called graphics controllers because they really weren't reprogrammable quite yet. So I left Intel and joined the startup 3DFX. And 3DFX was lucky because they had built a very high performance arcade graphics controller based on a memory technology that at the time that they brought it to market, basically the market for memory fell and the prices of these memory devices fell through the bottom. And that made it possible that 3DFX had a product that was really targeting very high-end arcade games, but suddenly it had a PC price point. So 3DFX basically ruled the 96 to 98 timeframe with a design that was 10 times faster than anybody else. So I joined them in 98. And we were working on the industry's first programmable pixel shader architecture, Rampage. Fantastic design. We had some really impressive innovations, but it was one of those cases where we were too much too soon. And we never could get Rampage built to the spec that we set out to it. And that led to the demise of 3DFX. Fortunately, NVIDIA at the time was riding high, so they bought 3DFX and the design team that was behind Rampage, and that became actually the GeForce FX and a couple of other pieces, like all of the video processors that NVIDIA has after the GeForce pieces all came from the work that 3DFX did. So I spent 2000 to 2006 at NVIDIA, and at the time, NVIDIA was doing the Xbox project. So the team that came over from 3DFX basically finished the Xbox project, and that Xbox needed a chipset. And since everybody knew that I came from Intel and had been working on chipsets, they stuck me on the N-Force chipsets. And we did actually build 3 generations of chipsets that were absolutely head and shoulders above anybody else. They won every single award that was given to PCs and platforms. And on top of that, we also enabled AMD with very high performance chips and chipsets. The last couple of years at NVIDIA, I was working on Tesla, which was the first GPU. And that was sort of an observation that when we were looking at how GPUs were being used, people were actually using them for more general purpose computes, in particular lighting, because the GPUs were still very useful in sort of rendering tasks, but global illumination is a much more complicated computation than the GPUs were doing in hardware. So people were trying to use these GPUs in these much more general terms. So Tesla was a fantastic project in the sense that it was the first GPU. It introduced CUDA to the market, and at the time, the vision was that by 2007, 2008, that would be $1 billion market. So when I heard that, I actually felt that I knew a little bit about how to build very fast computing machines. So I left NVIDIA and started Stillwater. But before I tell you that story, I wanted to sort of take a step back and take inventory of what just happened, right? I have been part of this industry since the 90s, really, as a design engineer and an architect. And you see that there is this wonderful progression of progress in the semiconductor manufacturing process that the designers would be able to take advantage of. And everybody sort of understands everybody probably heard of this thing called Moore's Law. And the left hand side graph here is actually the original doodle of Gordon Moore, who was actually a founder of Intel, who had observed this phenomenon that every 2 years, the number of transistors available on a chip would double. And the right-hand side is actually a graph of what has happened from the 70s to 2020 that actually confirms that trend. It's going to get harder to continue this trend. It still is, pretty much available, but now other effects are starting to attenuate this process a little bit. But at the same time, the complexity of these designs that we can do at the very high end is phenomenal. There's a company by the name of Cerebras who actually said, okay, well, one chip is not enough. We'll just do a whole wafer. And they integrated all these die on the wafer together, and they have a chip that is 40,000 square millimeters in size. And that is an example of sort of the things that you as future designers can expect to work on. So as I indicated, when the GPU sort of came of age, I felt, okay, I know a little bit about building graphics controllers, but more importantly, the research that I had done in the 80s about custom hardware accelerators for complex real-time and high-performance computing applications, I started Stillwater. And at Stillwater, we are designing what we call software-defined supercomputers. And the basic idea is that we're talking about high-level synthesis, but this is really done at the parallel algorithm level. So this is not silicon, this is not logic synthesis anymore. This is really system-level synthesis. And at Stillwater, we built these things, but deliver it on FPGAs, on fabrics of FPGAs. So you are sort of part of a large supercomputer installation, but the back end where you actually do your high performance computing is done as a custom hardware accelerator that is delivered as a fabric of FPGAs. In this work, the opportunity arises to also start innovating in terms of arithmetic. And because the last couple of years, last half decade, I've been working on alternatives to IEEE in order to solve exascale reproducibility problems with Stillwater, people knew me and my research around this arithmetic piece. And the founders of Lemurian are also working on custom arithmetic, but this time to try to solve the problem of energy efficiency for deep learning. So they reached out late 2021, and the team and I clicked very well because I had been working on high performance accelerators with custom arithmetic. They were working on high performance accelerators for the robotic space. So it was a match made in heaven. And now we're working on delivering these type of techniques to the robotic space. So what I want to say sort of in conclusion here is that we've seen basically 40 years, 50 years, if you include the early IC designs, a rapid progression of capability. And that capability leaves you with complexity that the engineering processes need to figure out. And techniques such as SystemVerilog are techniques that are trying to control that complexity with higher productivity in the expression of the circuits that are necessary to design for the next generation. Personally, I am working on these two extremes, the planetary scale supercomputers for very high performance applications that model weather, all the way down to autonomy in the robotic space and everything in between. And I believe that those two trends are so economically valuable to every company in every country in the world that the opportunities for hardware designers that are skilled in building these systems with the tools that are provided to solve these complexity problems, the world is going to be an incredibly satisfying and intellectually stimulating environment to build a career, like I have done in the past 40 years. So with that, I thank you, and I wish everybody a fantastic course, and Godspeed to everybody.
Thank you very much, Dr. Theodore. That was certainly an inspirational moment for all the participants present here. It was truly inspiring to hear about your story and the great contribution that you had made in the field of processor design. I'm sure it had been so exciting and thrilling to be part of everything, part of many important developments in supercomputing. And we wish you all the very best for your future at Stillwater Supercomputing and Lemurian Labs. The next session would be a very exciting one where you can walk through the steps of developing an electronic chip, how it all started, and where the technology is at today. The first speaker for this session is Mr. Abarajithan Gnaneswaran, who is currently a PhD student in computer engineering at University of California, San Diego. He is a proud graduate of ENTZ and formerly an undergraduate intern at CSIRO, Australia. He was an RTL design engineer at Lemurian Labs, USA, United States, before he started pursuing his PhD. The second speaker would be Mr. Kithmin Wickremasinghe, who is currently a master's student in electrical and computer engineering at University of British Columbia in Canada. He is also a proud graduate of ENTZ and formerly a research and development intern at Telix Systems in Japan. So guys, buckle up as Abba and Kithmin take you on this amazing journey.
Right, guys. So throughout this session and throughout the later of the course, we are going to teach you how to design these chips using modern tools. So to appreciate the extent we have come, let's go back like 50 years to the very first commercial processor that was designed. So 50 years ago, in USA, there was like a startup, which is basically Intel, right? So they were approached by this Japanese company, so called BCCOM, and this Japanese company was making calculators, mechanical calculators, like and other type of calculators before that. So they wanted to build something efficient, and they wanted to build a modern calculator with integrated circuits. So they reached out to Intel, which was a startup, And Intel had hired this guy, Patricio Page. So with that, they gave him the task of designing a processor. Okay, the first microprocessor like in the world. So Intel didn't think like it will be a huge success in the future. So they did not put a lot of resources into that. So basically they let one guy to do the whole thing. So he sat down and he designed the computer architecture for the whole design. So basically he designed the ALU and like all the connections and basically like ISA and everything, he came up with that. And then like he also, after that, he started designing the actual logic. So like it was a family of 4 chips. So he started building each chip one by one. So from scratch. So he started connecting transistors and by hand and to make sure like it matches what he wanted to do. Okay. So then after creating the schematic of transistors and their connections and everything, so now you have to actually make them into a chip, right? So nobody has done anything in this scale before. So, and Intel was a startup, they didn't have a lot of tools. So then like what he had to do was he had to create the layout by himself. Okay. So he hired a CAD engineer, so who was a mechanical guy. So he hired him and like both of them do this layout together. So this layout is basically like in silicon, you have different layers, right? So as different layers, you deposit ions, create transistors. So this you have to have an idea of like how all these layers fit together. If you look from the top of the chip, right? So that's called the composite layout. So here he has drawn like this one, the digital version of what he drew. So they were drawing in this kind of graph papers back then. Okay, so after you drew like some sort of this composite layout, then there was like no verification. Okay, so there's no verification tools, no testing. So 3 people had to go through this one by one, like to make sure like all the transistors are connected and everything will work. So it is not just the connection, but also size the transistors. If some transistors are too small, they will not drive current and the whole chip will not work. If they are too big, they will draw too much current and the chip will not work. So you have to try size each and everything precisely. So he did everything by hand again within 6 months. So after doing all that, the next one is the ruby cutting. Okay, so what he did was like they had this. This was the initial process. So you have this composite layout. On top of this, they keep this kind of tracing sheets and called a ruby lith, and they carefully like cut lines. So they extract each and every layer separately. Okay, so and each and every layer of this they like it's extracted separately, and that is used to build the mask. Okay, for the to make the actual transistors. So when you do this, like again after cutting all this, 3 people have to go through this like one by one independently, part by part, to make sure everything is connected. There are no mistakes. So then after all that, they send that to the fabrication, and over there like they created the chips. It came back and he tested it and it worked. Okay, it worked on the first try. So like and it was yeah, so that was the first commercial microprocessor. So it's called the Intel 4000 family. So 4001 is a RAM, 2 is a ROM, 3 is a shift register, and 4 is a CPU. So you can see this is the breadboard, the PCB of this particular calculator, right? So you can see all these are connected, and then like so this was released 51 years ago in 10 micrometers. Okay, so and 2000 transistors, about 740 kilohertz, right? So with this, like he moved on to the next project at Intel, which was Intel 8008, and this is the first x86 microprocessor. Okay, so you might know x86. It is running in every computer today. So like other than Mac. So you have all the Intel and AMD computers are running with x86 instructions. So this is the first chip of that, and that was derived from like his knowledge on this chip, this design, right? Okay, so we just saw how the first chip was made, but then like just like you said, you can see the Moore's law. So every year, every 2 years, the transistors have been doubling. Okay. So because of this, the performance has been going up and up. Okay. So how fast you can do things. So for an example, the phone in your hand is millions of times more powerful than the computer that put man on the moon. Right. So you can see the performance increase like 52% a year, 22% a year, and over the 50 years, it has gone up. Right. So why does this happen? Because the transistors get smaller and smaller and smaller. From 10 micrometers, we have gone 10 nanometers. So you have like about 1,000 times. Okay, have been smaller, and we are putting more and more transistors on the chip. So then we have this. Okay, so now the one of the biggest concern is Moore's law is dying. Why? Because we have from early days we have gone to the very small chips like this, 4 nanometers now. And when you go smaller and smaller, you have like quantum mechanical effects, and like you can't go more than a certain limit. So now it's like a couple of atoms wide, right? So if you each transistor is few atoms wide, you can't go less than 1 atom, right? So then the like Moore's law is about to die. So which is why we need like better designers, right? Better designers today. And now like companies like Apple have introduced new kind of techniques to increase power efficiency and everything. Okay, having performance goals, efficiency goals. They are revamping the whole architecture, okay, to keep on improving the performance the same way as before. Okay, so it's a very exciting field, exciting time to get on. So how is this even possible? Okay, so if the first chip was a house, okay, so today's CPUs are as big as a country. Okay, so by comparison, it's like 4.1 million times bigger. So in Sri Lanka, you have 5 million houses, right? So every year, each company, say Intel or AMD or anything, they are designing new chips and sometimes coming up with complete new architectures. And they are selling, they are doing all this process, and they are selling millions of copies around the world, okay, in your computers and everything, which are working perfectly, so flawlessly. So it is like every year you are designing an entire country from scratch and you are selling, right? So how is this even possible? Okay, you can't do this by hand, just like Pasindu did it on his time, right? So what made this possible is basically abstraction. So nobody today knows everything, okay, in the chip design. Okay, so you have multiple levels of complexity, like from the very bottom transistors to the very high logic and architecture. And only people will work on their own levels. So like mostly, so we need to know about everything, but still we work on our level, right? And you can reuse parts on different levels, parts of the design. So that way you can make improvements very fast. Then you have CAD tools, computer aided design, and they're very smart enough to optimize the logic. So you can write in a very high level. They do very high optimizations for you. Okay, so you don't have to manually do everything. And these CAD tools are like super expensive. So these are the Synopsys tools that we'll be doing in the course. They're super expensive because they have to be very accurate. So if they make a mistake, the company will lose like billions of dollars, right? So because of that, the tools have to be very accurate. And then you have industry standards like SystemVerilog is an IEEE standard. You have GDS2 file standards and all these things to make sure like the companies can work with each other, and they can reuse the designs, and they can do all these things. So that is how we are able to make so many chips, so advanced chips every year, right? So with that, I will hand over to Kithmin.
Thank you, Abba. So let me take over. I hope you can see my screen clearly.
Yeah, we can see Kithmin.
Okay, thank you. So yes, thank you for inviting me to do this section of this presentation. I've been having a really great time listening to the speakers today. And I don't think Abba even mentioned this, but both of us got up at 5 a.m. today to do this section, and it's really interesting. So I wanted to give you an idea about how this ASIC design flow or the process happens. And so far, everyone has been talking about the history, the interesting history, and all the developments that have been happening in this field. And it's really interesting to know how this, engineers and the industry has developed this process up to now. And it starts with this topic called standard cells. So standard cells is a group of transistors and interconnect structures that provide a Boolean function. So you might have heard of these Boolean logic functions, right? Inverters, or NOT gates, AND gates, OR gates, NAND gates, NOR gates, and such, and also storage functions using flip-flops and latches. So these are some examples of standard cells you can find. So here, NAND3 and NOR3, the 3 stands for like 3 inputs, right? And let's kind of like focus on this first standard cell for convenience. It's the inverter standard cell, or the NOT gate. So one other thing to sort of refresh on. So everyone has been talking about layers of design, right? So we are focusing on CMOS transistors. CMOS technology has been rapidly developing, rapidly developed over the past 4 decades, I think. It has actually been one of the semiconductor industry has been one of the like fastest developing industries in human history. And you can see here an example of this inverter or NOT gate designed on CMOS using NMOS and PMOS transistors. And what this looks in terms of like deconstructed in terms of layers is seen here on the right side of the slide. You can see the different layers that have been gone into developing this transistor, right? So there's the transistor layer, metal, and via, and also kinds of layers, and it's called like a layer stack, right? But the important thing that we want to begin with is how to design these standard cells. And this is not the focus of this course, but it's a really interesting topic that should be covered in order to get into the ASIC design process. So there's this thing called technology node, or the process design kit. So there's different levels of nodes that have been developing over the past year. So you saw the Apple Silicon chips, right? So from 90 nanometer to 4 nanometer, these nodes have been shrinking rapidly each year. And the latest iPhone actually has like 5 nanometer or 4 nanometer node chips in it. And these are developed, these nodes are basically like defining these process design kits, right? And they have their own design rules, and we hire expert designers or expert like engineers who have been trained in these areas to design the analog designs. And we use tools such as like Cadence Virtuoso for these analog design tasks. So Cadence is like a separate area where you have to like get the separate level of training to use these tools. And in that process, you go through different levels of, I guess, like design in order to achieve one of these standard cells. So let me just like go through that very briefly. So there's like gate level schematic design, simulations at the gate level, and you make sure that everything works out. And then you go into layout design, you lay out all your transistors, and then do a physical verification with design rule checks, layout versus schematic, and then parasitic extractions, and you make sure that everything works in the circuit level before you do the test structure fabrication, as well as evaluate process corners. So standard cell inverter design process in 45 nanometer GPDK. This is an example from my supervisor's website, actually. And you can see here a kind of like a step-by-step of how this was done using Cadence Virtuoso. And you start with your schematic and you end up with the layout, which you can, once verified, you can send it for small tape out, and you can measure the chip as well. So this is kind of an example of a standard cell design, and you have to develop standard cells, kind of like a library of standard cells, in order to actually do a great job on designing like different kinds of logic designs. So let's start with the logic design process, right? So you get a set of specifications to design something kind of like a requirement. So here, this is like a Pentium process architecture. And basically you have different kinds of things that you want to do using logic design. So for example, you might want to develop your own kind of state machine. And you can begin by using these kind of state machine like flow diagrams. And there's like different ways you can define your diagrams, and you come up with an architecture design for what you want to design. So you, based on your specifications, you know what you want to design, and you have to begin to sort of lay out how you want to design it. And that's where like SystemVerilog and those kinds of description languages come in, hardware description languages. So you do logic design using SystemVerilog, VHDL, or other types of languages. And in this course, we are specifically focusing on like a variety of different cases which you can use to learn this logic design process. So here's an example of what you would go through in the FIR filter design. We'll be covering this course. And not only just design, there's a component included to do the verification as well. So there's a test bench design and then simulating to make sure everything works out. So you can see here the simulation process involves this kind of layout as well. And then you do the next step, which is synthesis and generating a Verilog netlist. So you're just going to use the code that you wrote using SystemVerilog, and you're going to map it to the existing standard cells in your library. And you come up with this kind of a netlist and like this kind of connection diagram. And then you can also simulate that again using your test bench design, and you ensure that it works with the gate level verification as well. Once you're done with all those two sets, you can go into the place and route, which is where you define kind of like a layout for your IC that you're designing. And you do some, first you do some like VDD and VSS rails definitions for those and the area. And then you start placing your standard cells inside this little area, and then you start routing them. So everything happens using software, and you can sort of like optimize how you want this done, and then you do the pin placements and everything. So here's a kind of a zoom in of the GDS2 file that comes out from this process. So you can go to the source and read a lot more on that. And here in all these three processes or the steps, you can work with different kinds of tools. So every step has kind of its own optimized tool to deal with the complexities and the obstacles that you have to face when you're doing your own custom design. And finally, the very interesting thing that happens is you do the fabrication. You have to get access to like these foundries that do these chips, the designs on the silicon wafers, and you obtain the final outcome, which is silicon die. So you can see here an example of that silicon die, and you do the wire bonding. So you have these like metal or the gold wires that are like sort of like soldered or connected to these pads around the chip, and these wires are then like connected to the packaging, and this kind of packaging process happens before you get your final electronic chip. So it's a really really complex but very optimized process, and people have really sort of fine-tuned this process over the years, and it's a really booming industry right now. And there's actually a lot of room for demand for really good engineers to actually like work on these areas of this ASIC design flow. And in this course, actually, we are really focusing on logic design and getting you guys started in the foundation of this flow. So I hand over back to Chatuni, and I hope all of you got a good idea about this complete ASIC design for process. Thank you.
Thank you very much, Mr. Abba and Mr. Kithmin. That was truly an exciting session where we got to know about the intriguing milestones in the history of electronic chip and valuable insights into ASIC design process. So thank you. Moving on, next we have our second keynote speaker for the day, Mr. Fahmy, the Director of Research and Development at Synopsys. He graduated with flying colors from the University of Peradeniya with a bachelor's degree in electrical and electronic engineering in 2003. He completed his master's degree in advanced computing from the University of Colombo in 2009. He started his career as a software engineer at Design Soft Technologies in 2003 and became a senior research engineer at Dialog, University of Moratuwa Mobile Telecommunication Research Laboratory, and a senior software engineer and a team leader at Excel Technology Lanka. Making his way into the management field with a strong technical background, he became the engineering manager software IP course at Tire Logic in 2008. In 2011, he joined Atrenta as an engineering manager and made his way up to be the director of operations in Sri Lanka. He joined Synopsys in 2015 and serves as the director of research and development to date. He is truly a competent software engineer and a great leader. Sir, I am privileged to invite you to deliver the keynote speech.
Thank you, Chaturi. I hope you all can hear me clearly.
Yes, we can hear you, Mr. Farazy.
Okay, so I hope you can see my screen as well.
Yes, sir.
Okay, thank you, and good evening, good afternoon, good morning to all of you. I see people around the world have joined this call, and it's amazing to see all of you joining this session. So we had some very good lineup of sessions where we heard about what is an electronic chip, how they are designed, what is an EDA tool, Moore's law, etc. So during next 20 minutes, I'll try to summarize some of these concepts or some of these things what we heard and give more insight about the industry. Also, how Synopsys has impacted the growth of innovation. So as we all know, electronics have become an essential part of our day-to-day life and is found in almost every application that we use, impacting everyone, everything, everywhere, and everything. Whether you are a newborn baby or whether you are a person in the support system, you still need electronics. It's as you can see this picture that is impacting mobile, Internet of Things, industrial, digital home, data center, automotive, etc. And this industry is a huge industry. There's I think more than $1 trillion is circulating in this. It's $1 trillion industry. And a lot of companies are coming up with electronic products. For example, the companies like Toshiba, Panasonic, LG, Siemens, Tesla, even the automotive companies, the mobile companies, appliances companies, all these companies are coming up with various products that's helping us to make our lives easier, helping us to do our day-to-day work much easier. So one essential thing in these electronic products is the integrated circuit, or we call it the electronic chip. So the companies that design these electronic chips are called the semiconductor companies. So the companies like Intel, Parakum, Samsung, Apple, Toshiba, all these companies, they manufacture the electronic chip, which is used by the electronic products. It is used by the electronic product companies to design their products. Now, in the previous session you saw, to design these complicated or complex electronic chips, you need some software tools or some software and hardware tools, which we call the electronic design automation tools. The companies like Synopsys, Cadence, Siemens, Graphics, that they all have different kinds of EDA tools, which will help to design these highly complex electronic chips. So now let's look at some of these things. So let's look at how these electronic chips have evolved. If you look at, here I have put some table, very basic data for you to understand. So here you can see the size of the chip has remained same throughout the last 50 years. If you look at the number of transistors that have gone into this chip, right? Earlier presentation mentioned that the first chip has only about 2,000 transistors. Then Intel Pentium 4 had 42 million transistors, and then it has grown tremendous. And today, if you take the Apple M1 processor has more than multi-million transistors, and also if you take the Cerebrus chip, it has more than 1 trillion transistors. So this is an exponential growth in the number of transistors used per chip. So you can understand that a lot of innovation has gone into this to increase the number of transistors in the same die area, in the same size. So this was predicted by a person called Gordon, who was the founder of Intel. So he came up with the Moore's law. He stated that the number of transistors on a chip would double about every 18 months. This exponential curve, or its exponential growth, was predicted long back in 1965. And until recently, we have seen this happening. So, and this exponential curve has helped many other technologies, many other innovations, and it has driven exponential growth in many technology innovations. So during last 50 years, we have seen many various industries, many industries going in this exponential growth. Let's take one like the computation. The computing power invented in 1970 was a very basic, it was a minimal set of instructions. And today, if you take the server computing, computation has increased dramatically. Similarly, the network, earlier it was very few computers, maybe 2 computers, started with 2 computers, and today we have the internet. And then the mobile phone, you have seen the first mobile phone, and today you can see the mobile phone that we have, and the amount of capability, technology, inside that. And also an extension of computation. Today we have the cloud, most recent one. All these industries have shown an exponential growth in their area. So one thing to keep in mind, all this was made possible by one thing. That is the great chips that has been designed by engineers like you. For the last 50 years, engineers have worked hard to come up with great chips, which has helped the exponential growth in all these industries, which has helped to drive the innovation value chain in the world. So these great chips cannot be designed in isolation. So you need to have a pretty good support system to design these electronic chips. So first of all, we have to invent the technology. We have to invent the technology to scale, and then we should know how to manufacture this. That is going to be the essential part, and it will get multiplied by the EDA tools, IP, and the test tools that we have. So once these are multiplied, you get these great chips. So here, yes, we would like to take some credit or a little bit of credit as the global leader in electronic design automation. Innovation in Synopsys has contributed to the technology advancement in the past 3.5 decades. So with the yes-if mindset, Synopsys has delivered many technologies to support the exponential growth. We can say we have delivered 10 million productivity for the users of Synopsys tools. So you can see that here the exponential growth, our tools have helped to support this exponential growth, and which means we Synopsys will continue to catalyze the exponential. For many years, the scale complexity delivered by Moore's law served to address the innovation demands of the industry. If you could migrate from one node to the next technology node, you would enjoy low power, high performance, and low cost, thanks to the smaller die size. So until recently, the technology supply and innovation demand was in balance. As we approach the current day, we see that Moore's law is slowing a little bit, specifically when it comes to 7 nanometer, 5 nanometer, 3 nanometer, 2 nanometer. Though the area is scaling, performance and power are not necessarily scaling as expected by most. Migrating to the next process node is more complex, it's becoming more complex and expensive. And the performance and power benefits are not coming. So while Moore's law has slowed a little bit, it's not dying. I mean, we don't believe it's dying. It will continue, but it has slowed down. The ambition of the market and its innovation demand remains. You see a lot of push people, a lot of demand for innovation. It continues in the same exponential flow. The widespread deployment of smart everything, demand in AI, automotive continues to grow. And all this demand is pushing the innovation, which pushes the companies like Synopsys to come up with new ways to think on how to keep up the exponential curve. So what can we do about this to keep up the curve? So this is where the era of SysMoore comes into the picture. We started looking at the systematic complexity of these tools. So here you can see, as I mentioned, the demand is increasing in high performance computing, networking, mobile, automotive, industrial. And then we got about the systematic complexity in SysMoore era. So some of these examples, the SysMoore era has created significant challenges. We call them technomic disruptors since they impact both technology and economics of product development. Various innovations are happening to push up the Moore's law and keep the curve with SysMoore curve. For example, earlier designers thought about the power towards the end of the cycle. In the timing closure, they thought about the power, but now there are tools being designed to think about the power from the beginning, even from the architecture. So as you know, there are a lot of communication happening between dies, die and memory. So now there are technologies to stack the dies one on top of each other so that the communication is better. And EDI algorithms were traditional algorithms. Now with AI and a lot of data, with AI technology, these EDI algorithms we use AI technology to give better results, to better give placement, better area utilization for the users of EDI tools. So there are various technologies that is coming up. Companies are working on to push this curve up to keep up with the SysMoore curve. There are substantial investments required across the product development spectrum from silicon to software, to keep up with this, SysMoore curve. A lot of investment is happening in this area. Some of these examples, I think, from Synopsys. Right. So we begin with silicon level techniques to co-optimize the design and technology, and then library co-optimization, and then various tools to keep up with the chip level demands. The tools like DSO-AI is used in AI technology to give better area utilization for the users. And at system level, there are many challenges found in safety, security, and power optimization. And software level, people are worried about, again, security and vulnerabilities of areas. And also, in addition to these tools that is, developed or innovated by Synopsys, we're also thinking about the backbone technologies like using cloud architecture to scale computation, and then use data is coming up from all these design processes and all these tools. So Synopsys will continue to invest in breakthrough innovations to support the market bigger. And if you look at the market today, so change is happening across many markets. So we are seeing, significant change in many markets, whether it is automotive, mobile, networking, data centers, enterprise software, healthcare, financial. We see a dramatic change happening in all these markets. In all cases, there is growing demand for smart everything. So, as you know, you all are moving towards a smart world. Smart everything is becoming the driving factor. And the hyper-connected world is generating a lot of data. You need very good machines to analyze this data and give results at the edge and also at the centralized places like cloud. So there's huge opportunity for engineers to do the improvement and tackle these challenges. So in essence, smart everything is creating new challenges and opportunities for all of us. So what are the macro trends? Let's look at some of these macro trends in the world. In this new innovation paradigm, software is driving differentiation and delivering new innovation or new innovative user experience. There's a lot of software that is coming up, which creates the differentiation. People are using software to create differentiation rather than their built out for this. And chips are delivered the underlying technology to bring software to life. The widespread use of a dedicated AI processor is one example, and I spoke about some of these chips that have been developed. Massive chips are being developed to bring value to the users. In most cases, we have seen that chips technology and software have been working in isolation, but if you have systems where you can work these two together, where software and chip technologies can work together, that will create a lot of value in the future. The companies that can do this will be beneficial and they will succeed, and also the great products will come out when these two technologies blend together. Both software and chips are very powerful technologies, and then they will transform the world to the new era that we are envisioning. Okay, so these are some of the, I'm going through some examples of each of these areas. So, for example, if you take Starbucks had a very good revenue growth from year 2003 to 2008. Their chain grew a lot, and then they had a very good revenue growth. But they realized that their supply chain is not able to cope up with the growth. And then at that point, to differentiate their product, to make sure that customers are getting the best coffee on time, making sure that their outlets have enough coffee with them, they had to come up with a very sophisticated supply chain system. So we invested a lot, starting from 2008 on this, and they came up with a very good supply chain management system, which helped them to continue their growth. Similarly, Johnson & Johnson, I think in 2016, they were alerted with a security breach on one of their insulin pumps in 2016. So with that alert, it was a eye-opener for them, and they started investing in cybersecurity. Because, as you know, in healthcare, if people don't have the confidence that these systems are secure, they will not go into that. So, Johnson & Johnson started investing a lot on cybersecurity to make sure that their systems are secured and give confidence to the users that their systems are secured. And then let's look at the chips. As you know, some of these companies, Google, Microsoft, Amazon, all these companies, the software companies, but now they design their own chips because they have realized that is the way for them to that is the way for them to scale. So look at all these companies, even companies like Volkswagen, automobile companies, they have started investing a lot in designing or developing their own chips. Then I was talking about the third angle where you can optimize both the processors and then the chips. So that is if you take the kind of things that Apple has done, right? So they are one of the most valuable companies, and they optimize their hardware and software that people will, the users, the consumers will get best value. Similarly, Tesla. These are some of these examples where companies optimize the hardware and software, the chip and the software part, to bring value to provide value to customers. And I would like to highlight some of the investments happening around the world in this area. So we all know that recently US government signed the CHIPS Act, that is to fund more than $250 to $280 billion to the market in the next few years for research and manufacturing of integrated circuits, or research and manufacturing of semiconductors. We know Intel is going to increase foundry investment in 10x in 2000, by 200 billion. They have already started working on the foundries in Texas and other sites in US. Micron announces the historic investment up to 100 billion to build a mega fab in central New York. India to invest 30 billion into semiconductor supply chain technology sector. Driven by high demand semiconductor market to reach 64 billion by. So this is in India, they are expecting the semiconductor market to reach 64 billion by 2026. This is from the ISA report in India. There's a lot of investment happening around the world. People have realized that investments in semiconductor industry and media tools is going to drive the innovation for the next couple of decades in the world. In summary, a new semiconductor ecosystem is here, driven by software and chips, and vibrant markets compelling innovation drive inflection point. Innovation demands is far greater than technology supply. Inflection point creates major technomic disruptors. Synopsys stands ready with ambition and investments to address the disruptors of the system era and catalyze smart everything. As a final step, few words, which means we need more talented, good engineers to work in this area. As a country, we have a great opportunity to get into this new era, especially being closer to India, knowing that India is investing a lot in semiconductor industry. It gives us a huge advantage to step into the era of smart everything, not as a consumer, but as a technology disruptor. Thank you to all of us.
Thank you very much, Mr. Fahmy, for that informative and insightful session. Synopsys is indeed a pioneer in silicon design automation, and its contribution is immeasurable. Thank you for leading Synopsys Lanka to develop and conduct research that immensely contribute to the industry of ASIC and processor design. Next, let me welcome back Mr. Abarajithan again to introduce you to the FPGA, which we call the flexible chip. And he will also bust the myths about SystemVerilog. This will surely be such an exciting part of our session today, as this would be the starting point of your journey in electronic chip design. Mr. Abba, over to you.
Okay, so to continue from the flow we have been discussing on, we had an insightful session from Mr. Farazy. So his company Synopsys Synopsys builds the tools that we are going to use in this project to build our chip, right? So at the beginning, we saw how the first chip was designed by hand, and then we saw how all the process of like building the chip step by step. And then this at the very end of it, we make the mask, the GDS2 files, and we are sending that to the foundry, right? So this process is done through using the Synopsys software, which are really expensive and rare to find. So after what you send to the foundry would look something like this. So this is the final placed and routed design. So if you see on the right side, you see how they did it in the first time. So by hand. So here we have something precisely similar, but again, it's done by the Synopsys tools, right? So you can have like the routing and everything. It's done automatically and very highly optimized view, right? So once we send this to the mask, like then we in the foundry, they fabricate these chips. So what are foundries? These are like located in Taiwan. You have TSMC, and then you have Intel in America, and you have like a few foundries around the world. So they actually make this chip out of silicon, as we know it. Okay, so we have they start with silica sand, and we have after melting it, we get the silicon ingots and wafers. So these are cut into pieces, the molten silicon. So these are like wafers, and then using a process called photolithography, they etch the different masks on top of the wafer. Okay, so at the very bottom we have the silicon substrate. On top of it, they they deposit different chemicals for doping, as well as in a different layers you deposit silicon dioxide, remove it, and so it's a multi-layer process. Okay, so for every layer, the masks that we designed through these tools are used to control how the chips are made, right? So at the very end of it, like you get like a big wafer of a lot of chips, which are cut into pieces and like packaged. So these are the fabs or the fabrication plants where these things happen. So you can see these are some photos from Intel. So Intel fabs. So this you can see like people are wearing this sort of fully covered dresses because these are called clean rooms, right? So the entire fab or like a huge area of the fab is considered a clean room where they have like very few particles per square meter, right? So the air is filtered to make sure like nothing else get deposited on the chips during manufacturing, right? So this is the kind of wafer with actual chips. So yeah. Then how are these made? Like the actual machine that makes the chip. Okay, so each machine that makes a chip. So it's all made from one company. Okay, so there's like ASML. So it's a Dutch company, which in a sense, it runs the world, right? So they are the ones who make this photolithography machines for all the foundries, and they do all the service and everything. And they are the ones who are pushing this nanometer progress, right? So for every from 65 nanometer, 40 nanometer, so today up to we have 2 nanometer. So like that, at every step, they have to redesign like the process, and they have to improve it to make sure like they can make transistors at very tiny level accurately without any faults. Okay, so this each machine costs like $400 million. It's really expensive. So and all these are made by one company, ASML. Right. So it's insane that humans can draw tiny pictures on a rock and zap it with lightning and make it do crazy math. So if you think about it. So then the question is like, now you have know about the process. So the question is, can I do this? As a student, can you do this? Or an engineer? So of course you can. So these are some venues like that have opened up quite recently, a couple of years ago. So this is sponsored by Google. It's called eFabless. So you can Google it, and they help you to make chips for free, right? So every year they have shuttles. So now they have had eight years they have done this, I think. So you have 40 slots per shuttle. So you have to submit your design, and they select 40 best designs. And they it has to be open source design, and they they fabricate and give you back. So the PDK will be 130 nanometer open source. Okay, so it is not the latest one. You can't make things in 2 nanometers, of course. So this is like a quite old PDK, old node, and at the same time, the tools they use are open source tools. Okay, so open source alternatives for the entire flow. Okay, so but then then there's another one called tiny tape out. You can check that out as well. But then this is not ideal because you can't have like big designs, and then these open source tools are not very completely polished. Okay, they are still in the process. So unlike the Synopsys tools that we are going to learn today, so which are highly optimized and very productive. So then you have some issues with this, and other than that, you have like only you can make small designs. Okay, very small designs. So you can't make anything that is useful or like any new or something like that, right? So then, what is the solution? Okay, so solution for that is the FPGA. Okay, the soft chip. So what is an FPGA? So if you look at it now, this is the development board, FPGA development board, and this is the actual FPGA. So which is a chip, and this is the entire die. So FPGA itself is a chip. So if you open this chip just like we did before, inside you will see something like this, which have like very regular pattern. Okay, so you can see very repeating blocks of this one. Let's see what it is. So FPGA is basically field programmable gate array. So you can think of it as a meta chip. That means it is a chip where you can implement your own chips. Okay, own digital circuits inside this chip. Okay, so how does it work? So it works something like something like ASIC. ASIC is the application specific integrated circuits. So which we have been talking about all this time. So we saw that Kithmin told you about standard cells. You have AND gate, NAND gates, NOR gates, and pair gates, flip-flops, which get synthesized, right? When you're making a normal chip. So just like that, inside an FPGA chip, you have some standard cells. Okay, some standard things, which are one is a CLB. Okay, so this is a configurable logic block. So that has a lookup table. Okay. So an FPGA doesn't create things from AND gates and OR gates. What it has is it has small lookup tables. These are very small memories. They memorize your function. Okay, so if you have a logic function, they memorize the first table. Okay, inside the lookup table. That's how they work. So then inside like each CLB, you have a flip-flop, things like that. Then you have some special units like called DSP, which does some large additions and multiplications and everything. So then you have memory blocks like DRAMs, block RAMs and everything. So this is the pattern you see. So this is the repeating pattern you saw on the die, right? So connecting them is a switching circuit. Okay. So which means the connections between these blocks can be broken and reconnected. Okay. So let's continue. So that is the whole idea of FPGA. So what happens is when you want to implement your own chip, own design, the software will connect these different blocks in the way like necessary, okay, to implement your logic circuit. And at the end, what happens is the logic you want. For example, a small processor, you can put that inside an FPGA. Okay, so you can create the design inside the FPGA. It won't be as efficient as ASIC, but it will you can still test it in the real world. So then let's see why. Okay, why do you want to go for FPGAs? So you have this is the pros and cons. So if you see ASIC or custom silicon, you have only your chip, right? You have only your circuit. But in FPGA, you have some extra management circuit. Okay, just like you saw, you have some extra stuff, and you have routing circuits and a lot of other things. So because of this, an FPGA will not be as optimal as an ASIC. Okay, it will take more power than a custom chip. Okay, and it will run at a lower frequency than a custom chip. So in a custom chip, you can easily get like gigahertz. So just like processors, but in FPGAs, usually you get like 400, 600 megahertz that way. And you get it takes more power. And if you want to produce some chips, and if you want to produce millions of chips, then FPGA is more expensive. Okay, so it's better if you are going to make millions of chips, you go through this whole process you make the mask, you send it to the foundry, and then if you make million chips, one chip will be like very cheap. Okay, that's how we are getting actual chips, right? So for very low cost, right? But then the problem is like ASIC takes 6 months at least to implement. Okay, from RTL to you have to do all the verification, you have to go to every step you have to go, and then you have to check everything. So it takes like a very long time to make one ASIC. And then in an FPGA, so other than that, like after you finish it and send it to the foundry, it takes about 6 months, okay, for the foundry to make everything and send it in general. So in FPGAs, you can implement within seconds. Okay, once you have a circuit, you just press a button and like the FPGA will get programmed. Okay, your circuit will appear in the FPGA. Okay, so it's very fast. So which means you can debug and you can do things very fast. Now in ASIC, the errors can cost thousands of dollars. If you make a mistake and if the chip dead doesn't work, you just lost thousands of dollars. In an FPGA, that's not the case. If it's an error, you just change the code and you upload it again. Okay, you change your design and you upload again. And ASICs, like if you want low volume, that means let's say if you want like 100 or 1,000 chips only, then ASICs are expensive. Okay, so then FPGAs are cheaper. So these are the advantages. So either you want to prototype or else you want to go for like say 1,000 chips or something, then you work on FPGAs, right? So let's see some real world applications. So the first one is ASIC prototyping. Okay, so here you see the world's largest FPGA, which has 35 billion transistors, right? So this is a Xilinx Vertex, and you can see the size of it. So this is used to test processors. Okay, so you can put entire processors which you are going to make as chip, okay, which you are going to fabricate later. But what you can do is you can, before fabrication, you can put your same design into an FPGA. Okay, then the FPGA will become like that chip, and you can like test with your real world inputs, right? So that is one application. So another application is high bandwidth video processing. Okay, so anything that needs high bandwidth, you can expect an FPGA to do. Okay, so here you have like an Apple afterburner. So this is a macro, and the device you see here in the middle, that's the afterburner, and that has an FPGA, right? So you have data centers. So right now you have doing a lot of acceleration in data centers with FPGAs, and then like a lot of space applications. Okay, so for example, this is a Perseverance, the Mars rover, and you have other Mars rovers as well. So in especially in Perseverance, you have like a bunch of FPGAs which are doing a lot of computer vision tasks. Okay, so for an example, they're actually running some neural networks to, when you know how like this Perseverance rover landed in Mars, right? So it was using a sky crane and everything. So then the problem is like Mars is too far away. You can't control, or you can't like make decision immediately. So it takes a couple of minutes, right? So then because of that, you have to make decisions autonomously. Okay, human can't control it. So then all the landing spot selection was done by a neural network, and that was running on an FPGA. And then like it has self-driving capabilities. So again, from home, we can't actually control it. Okay, so we can, but if you can't drive it all the time, you will crash into something because it takes a while for the signal to go. So in between, like you give a command, it will automatically avoid obstacles and it will make its path and go. So all these are done on FPGA. Again, data collection, communication is done on FPGA, like all the like signal processing, those things, right? So the advantage here is like you have, why do they do this? Because in space applications, you have multiple problems. One is so you have in space applications, you have multiple problems. One is your space is limited, like inside, or your weight is limited. So here what they do is they have only one chip, one FPGA, and they can easily change the bit streams. Okay, so they like at one moment they implement the circuit which done digital circuit which does computer vision. Another moment they can implement a circuit which done some data collection. Okay, so like that you can switch the circuit as you want. So that is an advantage in FPGAs. So then you have like CERN particle accelerators. Okay, so this is the largest machine in the world, right? So it's in Switzerland, France border. So about 27-kilometer long tube that goes like this. You can see the scale of this. So this is a human being in the red circle, right? Okay, so this huge detector actually produces like terabytes, petabytes of data. So they actually run protons through this, and they collide, okay, at very near light speed. So when the protons collide, you get like tons of data produced within very short time. So when you get that data, you have to process it and very fast. So you get so much data. So what they do is they have a lot of FPGAs and ASICs around this, custom ASICs and custom FPGAs around this, which take this information, process it, compress it, and send it to the computers. Okay. So yeah, and then you have FPGAs in the 5G base stations as well, right? So these are real-world applications where you see FPGAs. So not just prototyping. Okay. So how do you make designs for FPGAs? So the first one is like the same step as ASIC, right? You have logic design and you have verification. Okay, it's the same thing as ASIC, and you write your like design like this, and you do your testing. So we will teach you through all these things, and then afterwards you have FPGA flow. So this is similar to the ASIC flow, but now you don't have like you don't have very big softwares. So usually you have like one software which does everything. Okay, the softwares are simple and they are easier to use. Okay, so for students and everything. So then you like it does the synthesis, it does the layout, and it does programming. The FPGA programming means putting a digital circuit into the FPGA, right? So and it does the simulation. So all of this can be done in one software. But then the issue is like you have resource constraint. Okay, so an FPGA has only limited number of resources, CLDs and everything. So if your design is too big, you can't put it. Okay, so yeah, so this is synthesis, this is the layout. Okay, or place and route. Yeah, so this is an example of how an FPGA works. So this is not our project, like it's something I found on in the internet. So you can see like, so this guy has implemented a video game on an FPGA. So again, like it's a custom circuit. So he has designed a circuit and he has put that circuit inside this FPGA board. And now he is giving inputs through buttons, and through that circuit is controlling the screen, right? So that's how it works. So you can do these kind of things. So it is really fascinating to see your own circuit working, right, on an FPGA, right? So then like FPGAs can be used for product development as well. So you test it on development board and you can build PCBs with FPGAs. Okay. So this, I told you this chip is the FPGA, actual FPGA. It comes with a big board for testing. And afterwards you can buy this chip separately. But then the chip is pretty expensive, but you have to strike a deal with the company to get it for cheap price. And you can make an PCB like this. So people have made it, and like a lot of people do. But it's much harder to make than regular PCB because it has a lot of wires and a lot of parallel things, right? So yeah. Right. So right. So with that, let's go to the next part, which is Mythbusters. So like, don't be overwhelmed by what we are teaching over here with ASICs and FPGAs. So if you're a beginner, we'll be teaching you all these from very beginning, very simple things. So you don't have to worry about that. So now for the people who have some experience in digital design. So we have a couple of slides to tell you about some common myths about the SystemVerilog language and like breaking them. Okay. So the very first myth is actually like Verilog versus SystemVerilog. Okay. So the thing is like a lot of people get confused. So they think SystemVerilog is a complete new language and like you don't need it and things like that. But SystemVerilog is basically Verilog for the past 14 years. Okay. So what has happened is like just like C++. So like other languages, you have Python 2, Python 3. So C++, you have a lot of 98, 9, 11, 14, and 17, right? So just like that, in SystemVerilog was created in, and it was merged with SystemVerilog as a radical improvement. Okay, so like C++ 11, SystemVerilog brings a lot of features to Verilog, right? So you see, these are the versions of Verilog from 84, 95, 2001, and 2005. So from 2009, there is no Verilog. Okay, so the language was renamed into SystemVerilog by IEEE. Okay, so by 2009 and 2017, what we have is this one, right? So you can see SystemVerilog is a superset. Okay, in this diagram, you can see it's a superset of the old Verilog. Okay, so what we have here is the 2005 features. These are the like 2009 and 2012 features, right? So which means you can change an existing Verilog file. You can change the name from .b to .sv and it will still work. Okay, so because it's a superset and the old features are still there. So if you want to, if you're familiar with Verilog and if you want to use some features, of course you can. But in SystemVerilog, they introduce new features which help you to write better code. Okay, so you don't have to use the Verilog features anymore, which are confusing Verilog features. You can get rid of it and you can use the simpler SystemVerilog features. That's the idea. Okay, so the next myth is like SystemVerilog is only for verification. So it is not only for verification. So this is the industry standard language for both hardware design and verification. Okay, so again in this diagram you see like half of the features, more than half the features are for design, and the rest are for verification, right? So testing. So you do both like in the same language, and almost every processor and chip you have seen like was likely designed with SystemVerilog synthesizable features, right? And was tested with UVM. Okay, so UVM is using SystemVerilog, right? So it's a source for that. So the next myth is like SystemVerilog is like assembly, it is unreadable and everything. So that is not the case. Okay, so this common myth arises from the fact that you have the same language can write different levels. Okay, so which means in using like Verilog, you can actually write the switch level, okay, the transistor level like things, and then you can write gate level things. You can connect AND gate or gate together, the net list. Okay, so you can make the net list also made with Verilog, and so this is like assembly, right? So this is what the compiler produces. Okay, so when you synthesize the tool, it produces this, but it's very hard to read. Okay, then you have the register transfer, RTL. So this is where you work with. Okay, we write high level logic code. Okay, so logic descriptions, and this one we use the advanced features of SystemVerilog to write the behavioral and RTL code. So these both are like high level languages like C++, and at the very bottom you have like assembly, like very hard to read code. Okay, and all of these can be written in the same language. So which is why it's often confusing. So some people actually write code like a synthesis tool, but you don't have to. Okay, so you can write code in a very high level and you can make it into this one. So the next one is like SystemVerilog is old, it's quite dying, and we have like new languages coming up. Okay, which is true. So we have like a lot of new languages that are coming up as a replacement for it. Okay, so you have in C++ based languages, HLS and Xilinx HLS, Intel, Catapult, a lot. Then Scala based languages, we have Chisel, Spinal HDL, Python based languages, MyHDL, MyRTL. So all of these are different HDL languages. Okay, and the HCL, hardware construction languages, right? So, and Kotlin based and Haskell based, you have two. Okay, so you have a lot of languages. So in 1980s, there were like more than 50 different languages, right? So HDL languages, and then VHDL and Verilog were created to unify them. Okay, they were introduced by the Department of Defense. So to unify like all these languages into some main response. So today, now there are like a lot of HLS and HCLs available. So they claim to be the future. So these HLS languages are mainly to attract, to convert algorithms, high-level algorithms like C++, written by software engineers. You convert that to chips. So they're working like that. And then you have like some advanced features in these languages as well. And they also compile to Verilog. Okay. So learning like SystemVerilog will help you to debug and optimize your designs. Okay, whatever you write in like HCLs and even HLS designs, it will help you to understand what is happening and it will help you to debug. So even if you are doing that, right? Then you have right now most of the new design and verification is written in SystemVerilog. Okay, so because it's the industry standard. So it is, if you are learning, if you're going into chip design, it is essential for you to learn like SystemVerilog, so you can be employable in most companies in the world. Okay, and it's important to be fluent in the industry standard language. Okay, so there are a lot of new languages there with a lot of advanced features, new features like object-oriented and everything. And but at the same time, you have to be familiar with the industry standard language while you experiment with the new language. Okay, so that's how you can get employment, right? So yeah, the next myth is like, I know VHDL. Okay, that should be enough. So VHDL is often used mainly to maintain the legacy code bases. And so some new design is being done in like Europe and in like the East Coast of US. So you have like VHDL 2008 is barely adopted by the tools. Okay, so here we have like a list of this is the source is this from Synopsys user group conference. Okay, so over here you can see like the different language standards that were both, and you can see VHDL is actually the 36. Okay, the new what the VHDL standard. Okay, so it was not being adopted by many because like they were using it for the old code bases mainly. So at the same time, learning SystemVerilog, like if you know VHDL already, like learning the SystemVerilog features will help you to write better code and opens up you to more jobs opportunities. Then there's a understanding that another myth that tools don't support SystemVerilog, which is not true. So again, SystemVerilog replaced old Verilog 14 years ago. So now in the past 14 years, a lot of tools have like included all the features of SystemVerilog. So every major commercial tool, okay, Synopsys tools, Cadence tools, and all the other tools, they Xilinx, everything, Altera, they support SystemVerilog today. And then you have some very few open source tools. They don't support some of the less used SystemVerilog features, and but they're still working on them. Okay, adding them. So you can see the issue pages on that. And this is a list of supported tools. And this is a Google project. So Google launched a project last year to make SystemVerilog 2017. That's the latest one, to make this one available on all the tools. Okay, so they are building a sort of front-end compiler for that. So because like this makes people very, very productive. Okay, so yeah. Then so then there's another misconception that students should be taught old Verilog first, which is also not true, because old Verilog is quite confusing. Okay, so one example is like reg is not a register. Okay, so we have some issues like that. Then SystemVerilog is more explicit. It's easier to learn. So you have flip-flop, combination, latch. So you know what you are doing, and the tool knows what you are doing. Okay, so it's more explicit, and you can write very short and simpler code than Verilog. Easy to design, easy to write, and easy to understand. Okay, so because of this, so students can and should directly learn SystemVerilog. So does this mean it's a perfect language? Of course not. So it's an old and bloated language. Okay, it has been there for like 20, 30 years now. So it has like a lot of old features, like they're still keeping it for backward compatibility to make sure they don't break any designs. Okay, so because of that, like the language sounds pretty complicated. And then because of this, it allows you to write bad code. Okay, so a lot of people who are familiar with old Verilog, what they do is they still write the very old long code. Okay, so because of this, like you will, when you join a job, you have to work with other people who write that code. Okay, so that will be a problem. And not all the tools support all the features. Okay, so you have different tools supporting different subsets, but most of the most commonly used tools, features are supported everywhere. So these are some issues. Then you have some painful to pipeline. So like that, and there is another like TL-Verilog which solves this problem. But with all these problems, SystemVerilog is the industry standard, which means you will have to learn this one way or another, okay, to be employable and to do things. So it's very important to learn it properly and be productive with that in design and simulation. So which is why we are doing this as the first course, where you can have like a hands-on experience and get comfortable with it. So does it sound familiar, like all these problems and everything? Yes. So that is like C++, right? It's the same situation as C++. So C++ is very old. Everybody hates C++, but it is the de facto language for high performance today. So similarly, SystemVerilog is like, it's bloated, but it is the like #1 language for design and verification today, right? So yeah, we'll have to learn it anyway. So then like some of you like who know this stuff, you might be thinking about UVM. So UVM is the set of predefined SystemVerilog classes and macros. Okay, so this is used for verification, so which you can pick the classes and build verification tools. Okay, it's an industry standard. Again, it's built upon SystemVerilog, right? So it's not synthesizable. So this one, we will not teach you UVM, okay, but we will teach you object-oriented like test benches, and we will teach you simulation. Like we will teach you the basics for that that's needed for UVM, right? So from that, you can go on and learn UVM later with that knowledge background. Okay, so we are mostly focusing on design and the simpler test benches using classes and assertions. So just like we saw before, verification is like a complete separate field. So there are like in the sense people actually go there, make a lot of money. The entire career they stay in the field. Okay, so by learning this, you are getting exposure to so many different fields, not only in design, in verification, and the physical design in many areas as well. Thank you, and over to Jasmine.
Thank you, Mr. Abba. That was indeed some very interesting stuff, especially about how ICs are fabricated and some cool applications of FPGAs. Thank you for busting the like the well-known myths of SystemVerilog most of the participants, including me, might have had. By now, you have a very clear idea about ASIC and processor design and why it is valuable to learn SystemVerilog yourself. The demand for engineers in the processor design domain has increased significantly. However, for that, engineers with the necessary skills must be readily available. That's why we are offering this short course on SystemVerilog for design and simulation. It is time for me to invite Dr. Subodha Charles, Senior Lecturer at ENTC, to introduce you all to this short course. He obtained his bachelor's degree from ENTC in 2015 and completed his PhD from University of Florida in 2020. In addition, he has held positions in Intel Corporation and Zone 24/7. Mr. Abarajithan will join him together with Mr. Pasindu Sandima and Mr. Sanjula Thiranjaya from Parakum Technologies to explain the logistics. This session will be followed by a Q&A where the resource personnel would answer all of your questions. So keep your questions coming through the link in the chat. Dr. Subodha, I cordially invite you to introduce our audience to the short course, SystemVerilog for Design and Simulation.
Thank you for the generous introduction, Chatuni. I hope I'm clearly audible and that you can see the screen.
Yes, we can hear you perfectly and see your screen.
Perfect. Right. I'm going to keep my video turned off because I'm actually in the middle of a power cut right now, so you won't be able to see me anyway. It's glad to see this many people joining for the introductory session. Now that you have heard about the industry, you have had a high-level overview of how chips are fabricated. Let me tell you how we are going to get started in this domain. So I'm assuming that there are people in the audience who are beginners, like absolute beginners, who are very new, brand new to this domain. And also there are people from the industry and academia who have some experience, even maybe experts to SystemVerilog. So we have designed the course such that we can create some value to each one of those demographics. And let me tell you how we are going to approach this and what you will learn throughout the process. So when we started thinking about how we can deliver the knowledge, because as you can see, it's a vast area and different people work on different subsections in this vast area, we thought of structuring this course like this. So in the title, you can see this is course number 1. So the reason for that is we are going to have a series of courses, which is why we are calling this the build your own CPU specialization. The course number 1 will provide you with the basics. And there are 2 more courses which will make you a very competent engineer in the domain of processor design. So the structure that we came up with is in course number 1, we are giving you the building blocks, the essentials, the basics of the language and the basics of digital design through a series of digital circuits that will contribute to developing an actual processor. So that is the focus of course number 1. You can see some of the things that we are going to deal with in this course. We are starting from the very basics, like a 1-bit adder, and then the complexity increases gradually. So even if you are an absolute beginner, we will make sure that you will be able to grasp these concepts and build on top of them. Then towards the end of the course, as you can see, we'll be combining things to develop a full system. So in summary, you will learn digital design and verification concepts. You will learn SystemVerilog features that enable you to write clean and efficient code. And at the same time, you will get access to Synopsys tools, which will facilitate the ASIC flow that we talked about earlier. In course number 2, what we will do is we will build a processor from scratch. So now in course number 1, you learn how to develop the building blocks. We will put together some of them and some additional items as well to build a basic RISC CPU. So RISC is an instruction set architecture that we touched upon earlier as well. Based on that, we'll be developing a custom CPU from scratch. We look at the ISA, the instruction set architecture, how we can put things together, the assembly and all that, right? And the language, the transitions, we will have a look at in course number 2. So the processor that we are building in course number 2, based on our knowledge from course number 1, it will be a functionally correct, but it will be a bare minimum processor. It will work, of course, but it will be very crude, meaning that there is scope for optimization. You can improve the speed, you can improve the energy efficiency. So there are scope for improvement. Of course, as you can understand, when we first build something, our focus is to get things working in a correct way. And then later on, we can think of how to optimize that. So that is what we are going to do in course number 3. Once you know the building blocks from course number 1, you put things together in course number 2 to complete the processor. In course number 3, we will learn the advanced topics, how to optimize things. For example, pipeline, out of order execution, right? So branch predictors. Some of these words might sound alien to you, but we will look at that and see how we can optimize this processor. So if you have heard the term computer architecture, we will be touching upon most of the concepts throughout these courses. So I hope the plan is clear to you. You are here today for the first course, that is the SystemVerilog course that you are developing. And then from there, you will be able to transition into these more advanced topics. And then at the end of these courses, you'll be a very competent individual in the domain of processor design. So let me quickly walk you through the course outline for course number 1. This is what you can expect when you go through the first course. So today we are conducting the first day, February 12th. So you don't see that in the list. What you can see in the table is what you can expect from day 2 onwards, starting from 18th February. So we have structured it like this. When you look at the table, you will see there are 2 main sections, one on the left here and the other on the right-hand side here. So on the left, you will see the sessions happening on Saturdays. And this time slot is this one, starting at 6:30 p.m. and ending at 10 p.m. Indian Standard Time. Right? So for those who are joining from other parts of the world, you'll have to do the time conversion accordingly. And the Sunday session will happen during the morning, IST, from 9 to 1 p.m. So what we are planning to do is, on Saturdays, we will look at the core content like the lecture. So this is where we will teach you, and also at the same time, we will work with you to understand these concepts. There will be some working sessions as well, but mostly this is where we deliver the content. And on Sundays, we will answer any questions, we'll go into discussions, and we will look into things in a more hands-on manner on Sundays. So as you can see, day 2, which is 18th February, we'll deliver the content. And the next day, which is 19th, that's a Sunday, 3rd of, sorry, not 2nd of February. 18th of February is day 2. Day 3 is 19th of February. That is a Sunday. We will conduct the office hours. So the office hours are where we answer any questions that you have, work with you on developing these things. It will be a continuation of what you learn on Saturday, right? So that's the plan. Throughout the 8 weeks, we deliver the content on Saturdays, we work with you, and we continue that with more hands-on things, answering questions, discussions on Sundays. So this will continue for 8 weekends, Saturday, Sunday, and before the new year, on 9th April will be our last day of the course, and we will have an in-person concluding ceremony at ENTC as well. So we'll wrap everything up, we'll recap what you have done. That will be the end of the course. So we plan to conclude everything before we go for the new year break. On 2nd April, we are planning to have a lab session. So this will be important because if you don't, that will allow us to meet in person as well. At ENTC, we will look at an FPGA implementation. Some of these resources you'll have to come to the university. So for that, we are arranging this in-person session. So you can see, I told you about the plan for Saturdays and Sundays. You can see this progresses day by day with increasing complexity, starting from the very basics. And then we look at the ASIC flow as well towards the end of the course. We'll touch upon the best practices and gotchas. That's like common mistakes, things that can be improved. This is the plan that we have for this course. So I think there is a link in the chat that you can use to send any questions that you might have about what we have planned, any questions specific to the content, what you can expect throughout the course. Please feel free to submit the questions that you have. Right. So I touched upon office hours already. All this content, this will actually develop, will be delivered through the digital circuits that we develop, right? So we did not want to just deliver content. We want to build things together with you. So this is where the capstone or the overall course project comes into the picture. Of course, the 1-bit adder and the n-bit adder, you can think of these as projects as well. But what I'm showing you here in the slide is where we combine everything together. Abba, would you like to add anything to this for the course project?
Yes. So yeah, so the course project, we have chosen like matrix system multiplier and axis stream unit. So if you're familiar with it, and then what with the UART serial interface. So the reason for this is like matrix vector product is like the fundamental operation, right? So today, like every single second, we are using like devices which are using matrix vector products, like AI, neural networks, scientific computations, all your video games, and then social networks, like all the Facebook and Google and everything, they have graphs, right? So all of these are done with this operation. So many companies are actually working really hard on accelerating this. Okay, like Google TPU. So is and the other companies as well. They are based on their chips are based on matrix vector multipliers. So you'll be building a matrix vector multiplier at the very end, and you will be like through gradually. And you have like at the same time, we'll be teaching axis tree as well. So axis is the bus that is used in all of your mobile phones and tablets. Okay. So any ARM device, you're going to have axis bus. So the axis bus is built upon axis tree interfaces. So we'll be teaching you the protocols and how to use. So we'll be touching upon on SoC design as well. Yeah. So through this course, you will be gradually building the system with the SystemVerilog, and you will be gradually testing it with SystemVerilog. with the test benches, and then you will take it through the ASIC flow, like using Synopsys tools. So you will synthesize, place and route, and finally get the GDS. And then like you will implement your RTL design on FPGA as well and test it in a real world. So that way you get some experience on that. Yes. So to continue with that, on day 2. So this is the first day of the session, which is next week. So we'll be starting from quite very basics. So you can see on every day that you will be learning some digital design concepts, design features and verification features. So for absolute beginners, like who don't know the language or who have not done this before, you will be learning all of this, like you'll be learning the design features from step by step, from very basic to advanced. At the same time, you'll be learning it through SystemVerilog. So then you don't have any problem, right? So you can learn it that way. That's the first language learning. The people who have experience in Verilog and VHDL, you will see these common design concepts. So you have seen adders, you have seen like ALUs and stuff. You will see how it can be done efficiently using SystemVerilog features. Okay. So that way, you will through this course you will learn to write better code, more maintainable like code that you can use. Okay. So in the first day itself, we will start with the 1-bit adder. So we will see how addition is done in a chip, and then we'll go on to n-bit rebel carry adder. Okay, big adders, and then like we'll make combinational ALU. Okay, so an ALU. So these are the things that you will learn through this, the design features and verification features you will be learning through this. So this for experienced people. Yeah. So on day 3 will be the office hours, and day 4. On day 4 we'll be starting with sequential circuits. So you have counters, okay, doing simple counting, and then we'll be looking at functions and lookup tables as well. And then you'll also look at FIR filters. So in the university, you might have studied about filters, digital filters and everything. So we'll see an example of how that is implemented in your earphones and your headsets and everything. All right. So that's one thing. And again, you'll be learning some digital design concepts, retiming and all, and some digital features and verification features from SystemVerilog. Right. So on day 6, we'll be learning the parallel to serial converter. So we'll be building a parallel to serial converter, which is used widely in all the designs, right? So in almost all the chips, you have something like this. So this is a simple example of the kind of teaching that we do. Okay, so we'll teach you the protocol. We'll have some animations and the state machines. Okay, so we will take you through this step by step, and then you will have like we will show you the code, and then we have what annotated, like how it can be, how it's the features that are there, as well as we will show some simulation and we will train you on this. Then we will help you implement the same thing again and test it so you can get some hands-on experience. So that's how we deliver this content. So yeah, so this you will learn some digital concepts like protocols and bus designs and everything. And on day 7, we start with matrix vector multiplication. So this will be like a fully parallel design. So you will learn to build a parameterized adder tree. Okay, when you're adding multiple numbers, how do you do that? Okay, as an adder tree. And then you will learn some again some design and verification features to like implement this thing. So this way, gradually you are learning more and more features, and you are like implementing them. That way you are getting more and more experience. Yes. So on the next week, we will be like we'll be doing converting any modules to XI stream. Okay. So XI stream, like it's a very famous protocol, as I mentioned. So if you can build a simple design and using the methods we teach you, you can convert that to an XI stream very easily. So we'll be teaching about skid buffers, and we'll teach about breaking long paths into like in pipelines and everything. So which way like your system works very fast. Okay. So you can have high frequency and how to put a lot of things together, like system integration. So we'll do that on day 9. And then on day 11, we will take this full system through the ASIC design flow. So you don't have to wait until day 11 to do this. So we are planning to give a document a few weeks in advance. So and we'll give you access to the tools as well. So which means you can use Synopsys tools for other examples as well. All the other examples, you can find a time slot and you can do this. Then on day 11, we will take this big design, and with you, we will take you step by step through the whole process. Okay. So that way, you can ask questions and you can learn it properly. Yes. Then on day 13, we will be looking at some common stuff. So resets and best practices in writing code. And then you have a SystemVerilog gotchas. Okay. So the easy mistakes that you can make and how to avoid them. Also, we'll be learning about GitHub actions. So this way you can automatically verify your design. So when you make your design and everything, when you push to GitHub, it will automatically run your test bench and verify your design. So we will learn that as well. So that will be very valuable for companies, startups, as well as academics. Then on day 14, we'll have a live lab session at ENTC. So we will implement this full system on the FPGA, and we will give you some experience with hardware debugging, right? So you will have FPGAs, and you will face some problems, and you will learn to solve them. So which is very important, right? So you will have a Python code running in your computer, and through that you will be sending data and doing the matrix vector multiplication, getting back to the computer to check. Okay, so this is it will look something like this. It will give you these boards and everything in the lab. Okay, on day 15, we will be talking about some advanced projects. Okay, so we'll discuss some of the projects that I have done, like system bus design and vision-based traffic control. So this is done on ARM plus FPGA, okay, processor and FPGA both together. And then also a DNN engine, okay, a deep neural network engine, so which is implemented on ASIC as well as FPGAs. So we'll talk about how those are designed and what are the things that you can do. Okay, thank you. Over to you.
Thank you, Abba. Right, so I hope that gave an idea of what we have planned for this particular course. As I mentioned earlier, the content will be relevant to both absolute beginners and current engineers in industry or academia who already have some sort of an experience about SystemVerilog and the related technologies that we're talking about. So from the very beginning, when we were designing the course, we did not just want to deliver the content. We did not want to go through the syntax of SystemVerilog, what it can be used for and all that. Rather, what we wanted to do is to teach you how to deal with the language through hands-on experience. That's why we have come up with a series of digital circuits that we'll be developing together with you. We'll face some trouble. We'll learn how to overcome those challenges. We'll learn how to debug. We'll make a mistake, and we'll work with you to overcome that mistakes, because that is what happens in real life. When you are an engineer, you have to make sure that you know how to identify problems, solve them, and learn on your own. So that entire experience we wanted to give you, rather than just telling you what the language is and what you can do with it. Which is why we have mentioned here, the digital design concepts are taught through examples and hands-on experience. Because another important thing is, when you're starting in a domain, you need to have confidence that you can do this. You actually can. We are not trying to artificially give you that confidence. We actually can. It's just that many people don't go into this area. But through the course, we hope we can spark some interest within Sri Lanka and motivate more people to go into this domain. Right. So we have structured the course in a way that we take small steps one by one until you become an expert. For the engineers in the industry, we'll give you the best practices. We'll tell you how to write clean, readable code, things that might take 1,000 lines of code to implement, how to do that in 100 or less. And you learn the best practices when you're working, so that even for the companies that can contribute to higher efficiency, it'll improve the human capital of the companies, which will enable the companies to pursue more projects and to work better in this area. So that is our motivation when putting the course together. At the end of the course, you will be familiar with these tools like EDA Playground, VS Code, and the Synopsys tools that we talked about, and some FPGA tools as well. So speaking in an outcome-oriented manner, these are the tools that you will be touching upon throughout the course. So when you are designing the course, structuring it, coming up with the content, we referred to this book by Stuart Sutherland. The person is involved in defining Verilog since from the early 1990s. Right? So he has about 30 years of experience in Verilog and SystemVerilog. He's one of the experts in the area. So we referred to the book written by him when structuring the course. So this person actually gets involved in advanced level corporate training workshops also. So he's a well-known figure and his content is quite valid. We combined our expertise with what Stuart had to say in his book and also in his other teaching and learning materials. So this is not the first time that we are doing a SystemVerilog course actually. In 2020, mainly with the leadership of ABBA, we did a course mainly for ENTC students, and we got a lot of good feedback for that. So that course was not as comprehensive as this one. It was shorter in duration, the content was less, but still we have about 3,700 downloads so far, and the content being downloaded actively every month. So that kind of gave us an indication that that course is quite valuable to the students, a good starting point. So we got some good feedback as well to provide more evidence to that. You can see some of the feedback. People from outside of Sri Lanka also have greatly benefited from the course. So this is one of the motivating factors for us to put this particular course together. So then what we thought was, okay, we did a shorter course. We learned some things from that, how to structure the course better. So with that learning experience, we have developed this particular course that we are offering to you right now. And the content also, it has been improved. We have introduced the Synopsys tools. We will tell you how to code better. We have also introduced some additional features in this particular iteration of the course. So we are walking through like 16 days of content that is much longer or resourceful compared to the first course that we delivered. So we hope this will deliver a better experience for those who are taking this particular version of the course. So we are glad about the support that we have received from Synopsys. From the very beginning, when we were putting this together, we got some valuable feedback from the engineers over there. We worked very closely, and we were delighted to have Mr. Farazy here with us today, delivering a keynote as well. So they have been generous enough to allow access to the course participants to the Synopsys tools. I don't know whether you know this, but these tools are like very expensive. These are multi-billion-dollar tools that are made available to you free of charge. The whole motivation is to get more people working in this domain, because we believe that Sri Lanka as a country has huge potential. Ms. Farazy mentioned the investments going into this area, and India is now becoming a very big player in this domain. So we wanted to make sure that we can also contribute as a country by training more engineers to take up these challenges. So we are grateful for Synopsys for being a part of it. We plan on enabling VPN access so that you can get access to these tools from your home, rather than you having to come to the university, which can be logistically challenging. So we'll give you the instructions as we progress through the course. The FPGA session will be in person, right? So I hope the difference is clear. Synopsys tools you can access from anywhere through the infrastructure that we'll be providing you, but the FPGAs are physical boards. So for that, you'll have to come to the university to play around with it towards the latter half of the course. If you're thinking about how you can complete the course, what do we consider as the end? Well, end will of course be day 16, but to make sure that you learn the content, we have an evaluation criteria. We put this in place because we'll be delivering a certificate for those who successfully complete the course. So to be eligible to receive the certificate, you need to complete the assignments. Don't worry, we are not taking attendance, meaning that if you have some other commitment, that is okay, but we highly encourage you to take part in the live sessions. But if you cannot attend for whatever reason, we will make the recorded videos available through the learning management system, that is Moodle. we'll give you more information about how to access Moodle during day 2, that is next week. So these are the team of lecturers that you will come across in the next few weeks, starting from some of the people that talked today also. Abarajithan, Kithmin, Hasini, Kaveesha, he talked in the beginning of the session, Sanjula, Pasindu, myself, and Dr. Ranga, who will be acting as supervisors for the course. So some of the people are joining from different parts of the world, mainly Abba from California, Kithmin from Canada, from British Columbia. So they actually have to wake up very early in the morning, especially for this session, I think after a couple of hours of sleep. So we are quite grateful for their commitment to deliver a very good course for the people who are taking part. So to wrap up, we'll then go into the Q&A. I think we are about 10 minutes late. I think we've planned to finish by 8:50. Sorry about that. The course is designed to be outcome oriented. I told that from the very beginning. We will be teaching the fundamentals together with real world applications, and we have designed the curriculum. We have custom made the curriculum, and it is, as you noticed in the previous slide, it is taught by a highly qualified panel of lecturers. A couple of other remarks before I conclude. The course will be conducted in English, if you're wondering which language you'll be using. And if you have any trouble understanding certain words, feel free to raise them during the sessions. We'll be providing you with Sinhala and Tamil explanations based on the requests that we get. So this is what you're looking at. When you complete the course successfully, you'll be eligible for the course. This is a sample, of course. The content here is not relevant to SystemVerilog, but this will be the structure. This is from one of our previous courses, the microcontroller-based embedded system design course, the sample that you're seeing, but the content will be different for the SystemVerilog course. We'll be giving some credibility for your efforts. When you complete the assignments and successfully complete the course, you can receive the certificate both as a hard copy, something you can touch, and then also as an online copy where you can go online and validate your credentials, the fact that you actually took the course. If that is useful for you in whatever context, the hard copy and the online versions of the certificates will be made available to you. So we hope you are convinced that this is a very important area to get into. It's a booming industry, so we wanted to provide you the necessary knowledge to enter that. We wanted to provide you with the hands-on experience and the job-ready skills for students and engineers to earn high salaries in dollars. The Western world, mainly North America, many companies are working in these areas, not just the big players like Intel, NVIDIA, AMD, not just those big players. Even there are many startups in this domain who are currently working in this area. So they are looking to hire people. And our goal is to provide more engineers with the capabilities. And some of these global players are present in Sri Lanka as well, like Synopsys, for example. So whether you work for a company based in Sri Lanka or for a company based outside of Sri Lanka, it can even be remote work. Because nowadays with COVID, people are quite familiar with working from anywhere in the world, not just based out of a particular office. So there are many opportunities in these areas, which has very high salaries, because this is a very niche area. There are not a lot of engineers. I mean, when you consider the world, there are, but in Sri Lanka, we still need more talent. So it's a highly paid position. We hope we will be giving you the necessary ingredients to get started and become an expert in this domain. Okay, so what are the next steps? I think that we have some questions on Slido as well. We'll use the remaining 15 to 20 minutes. We plan to conclude before 9:30, maximum 3 hours. So we have about 25 minutes left. I'll tell you about the next steps, and we'll be happy to answer any questions that you send in Slido as well. So to tell you about the next steps, let me go to the website. Bear with me for a second while I share the correct window. Okay, I hope you can see my browser now instead of the slides. This is where you can gather the information. So if you go to skillsurf.lk, you will see this landing page. You go to explore programs. You look at program details. This is the page dedicated for this particular course. We managed to build a cool video as well, by the way. If you have not seen, you can watch it. We had fun while developing this. Just an overview of what the course is. This is where you can find the details. So you can see view details on how to join the first free session. So click on that link. The text in the button will change, of course, because this is specific to this particular session. From day 2 onwards, this is what is relevant. Okay, so if you decide to continue from day 2 and further, it will not be this Zoom link. It will be something else. We'll give that information to the people who enroll in the course. So what does it mean to enroll in the course? That means you will have to make the payment according to one of these options and then complete this enrollment form. It's a Google form. We're asking for some basic details. So please submit that after making the payment using one of these methods mentioned, one of these options mentioned here. The account details are also given here, option 1, 2, and so on. If you are joining from outside of Sri Lanka, we've also made a Wise account available for you. Or else you can directly do a wire transfer, which will handled by the Uniconsultancy Services at the University of Moratuwa. So here are the payment amounts. For the students in Sri Lanka, this course will be given for 5,000 rupees. That's a very small amount compared to the content that we are covering here. And if you are a student at ENTC, you can audit the course for free. We are giving this benefit because we are conducting the course, mainly the FPGAs and the Synopsys tools and all that, and the lecturers who are part of ENTC. So that is why the ENTC students are getting the benefit. Every other student, we are giving it for a fee of 5,000 rupees. So how to prove your student status? We have given details on the Google form. Please go through that. And because Synopsys is sponsoring this by giving tools, there's a special rate for current Synopsys employees. And we have partnered with IEEE. Because of that, if you are a IEEE graduate student member or a higher grade member, there is a discounted rate of 20,000 available. If a particular company sends 5 or more people sponsored by the company or not, from a particular company, then there is a discount available for that as well. Everybody else, the complete course fee is 25,000 rupees for the entire 16 days of sessions, including the Synopsys tools, including the in-person sessions and everything. Okay, so please go through the terms and conditions also for you to get an idea about how we have structured and what we expect you to do while you go through the course. Okay, so we have given the link to the course website as well. I hope that gave you an idea about the next steps, the instructions that you need to follow. For any questions, this is our email and this is the point of contact on WhatsApp. You can reach out to Mr. Damit Khandage to clarify any questions, and we'll be working with him to provide you with the answers.
Sorry, Subodha, can I ask a quick question about international participants?
Yes, Professor Arjuna. Yes, we are glad that you are here. Please go ahead.
Yeah, so thank you so much for doing this. I really appreciate. And I know that several of the students at FIU are also taking part. So I noticed that you said in the program that towards the end of the course requires physical participation. Is there some way you can arrange something so that we can do the FPGA stuff here and still get credit for that?
Yes. So for those who are joining outside of Sri Lanka, that is not mandatory to get the course completion certificate. We'll be arranging a hybrid session so that the students can also see what's going on even if they join online. So that is the plan that we have for now.
Yeah, I mean, that's fine. But, we have FPGAs and others, toys here too. So there's no reason why we can't actually do it, provided you guys kind of manage that process. That's what I'm trying to say.
Perfect. Yes, thank you for the suggestion and also for the question. I think that clarifies for many people joining outside of Sri Lanka. We can work with you based on the people who are enrolling, because this in-person session happens towards the end of the course. By that time, we will know who is enrolled in the course. Based on that, we'll work with them to get the hands-on experience as well. If you have the devices over there at FIU, we can work with you to set things up.
Thank you so much, Subodha.
You're welcome. Okay. Yes, this is where we stopped. So I hope you are clear about the course completion requirements. We'll give you Moodle access, and the communication will happen mainly through the WhatsApp group. We will set it up once we know who is going to be enrolled in the course. So I think I took a bit more time than intended. We have about 15 to 20 minutes until we conclude. Let's go into some questions that we might have received through our Slido link. So while I get it up, you can feel free to drop any questions in the chat as well, or else you can submit the questions through Slido. Let me stop sharing for now. Let's go to Slido and see what questions we have. So for those who do not have questions or do not intend to stick around, you can feel free to drop from the call, but we'll be answering some questions from now on. This ends like the official proceedings. The remainder of the time we'll use to answer the questions.
All right, so I think we can start with the questions. I'm doing computer engineering, and which is more relevant to software engineering, and how much this will help me in the future. So computer engineering is basically like in the intersection of electronics and computers. So for an example, like I'm doing a computer engineering PhD over here. So I'm developing chips, right? So it's more towards computer architecture and stuff. So I think for you, this will be extremely valuable. So specifically knowing the architecture and how things can be built. So both go hand in hand, right? So that way, like, you know, like what is possible and how it's built as well. So I think it will be very useful for you. Yes. The second one, are we going to use software tools and environments throughout the course? Can we practice things without any hardware devices other than a computer? Yes. So we will be using the software tools, mainly Synopsys tools. So we will give you access early. So in the sense, a couple of weeks into the course. So that way you can, yes. So a couple of weeks into the course. So that way you'll be able to implement every example design in that in the Synopsys tools, and you'll be able to, and while during the course also, we'll be doing some online simulations using EDA Playground. So that way, like, you will be getting hands-on experience. So it's not like me teaching you, you will work on this by yourself. So I've heard FPGA helps in hardware acceleration. Can you explain how? So does it work like in GPU? Okay, so there's a big difference between GPU and FPGAs. So if GPUs are generally like, so you know, like in a processor usually has a couple of cores. Like you have like 3-4 cores, maybe big cores, and GPU has hundreds of very small cores. Okay, so which does some very basic operations like the ray tracing and these things. They're broken and delicate. But FPGA is like a blank canvas, which means you have to design your own circuit. Okay, so which means it is kind of more complicated to use it, which is what we are teaching. And by the end of it, you'll be very familiar with that. And that way, like, we will teach you how to implement efficient circuits. Because if your circuit is not efficient, it's not going to be as good as a GPU, right? So by the end of the course, you will learn how to do efficient things as well on an FPGA. To what degree assignments touch upon FPGA emulation, planning to deploy? Yes. So the largest, so we will be gradually putting things together. We'll be gradually testing, putting things together. And the final full system, we are planning to implement on FPGA. So maybe on that day, if you have time, you can implement the other smaller things as well. So, and you are always free to, like, if you are a university student and if you have an access to FPGAs, either in Sri Lanka or abroad, you can use that to implement other circuits also. Do we get use Synopsys tool chains on demand on a local license? Yes, what is the possibility of converting to these tools? Okay. So now the Synopsys tool chains, like, you will get, so the problem with that is like the Synopsys tools are extremely expensive. So the reason for that, as I mentioned, they have to be very, very accurate. Otherwise, the companies lose billions of dollars who are using Synopsys tools, right? So because of that, like they are quite expensive, but they give like free access to the universities and courses like this, so that the students like you can get trained. But after that, they don't give you like a lot of access, right? So, but the thing is, like, I think at this point, the tools have become kind of standardized. So Synopsys and its competitor Cadence, they have similar like commands and everything. And so at this point, the open source tools also will have like similar commands. They might be slightly different, but with the user guide, you will be able to quickly catch up. Okay. So basically the same thing, same commands, but might be slightly different. Okay. So that way you'll be easily, once you know the flow, and once you are familiar with Synopsys tools, which are the industry standard, then you will be able to download the open source tools yourself, and you can work with that as you want. So the next one is about VHDL. Is it the standard language in the industry? Okay, so VHDL is used in Europe. So it's used quite a bit in Europe and on the east coast of America. So you have like New York and Florida, right? So right now, and at the same time, we can see the SystemVerilog usage is increasing a lot over there. And just like the source I mentioned from the Synopsys conference, in companies, they are mainly using VHDL for legacy designs. Okay, so old, so you have like code bases which are like 20, 30 years old. Okay, so which are some efficient designs, very old designs. So nobody is going to rewrite that. So they still have the design and they're improving that. So for that, you have VHDL, right? But most of the new projects you are starting in SystemVerilog. So because you can write code much easier and more efficient in SystemVerilog. Yes. So the next one, do you provide learning materials for UVM? Okay, we can give you some links and we can give you some guides online, but UVM is kind of proprietary kind of thing, and it's quite complicated like on the verification side. So we will not be like teaching you UVM directly, but we can point you to resources like where you can learn UVM yourself based on the stuff that we are teaching here. The limitations of auditing the course, you will get the whole experience other than the certificate. Okay. And if you're already in ENTC, then what? Yes. So you'll be able to do the whole thing, but you won't get the certificate, only that. Yes. So the foreign people who are foreign joining from foreign, so we answered that. So you can use your own FPGA lab and we will work with you to get this experience. On Sundays, can we meet physically or it's online? So currently we are planning to have like online Zoom sessions. So like you can join there and we can ask discussions. And while we are teaching as well, in that time also, we will have the slide open. So you can ask questions. So it'll be very interactive. So it's not like a lecture, right? So in Sri Lanka, do we have high demand for jobs? Okay, that's a really good question. So yes. So in the way, what we have a lot of about 6 companies in Sri Lanka which are doing FPGA work, okay, electronic companies. So they're designing FPGA cores, and like Parakum is collaborating with some Silicon Valley like unicorn companies. So that way, like they're doing a really good job. Okay, so there is a big market in Sri Lanka, big potential for hiring people. And a common concern we heard from these companies is it is hard for them to hire students. In the sense, there is demand, but students don't. The students who come out don't have the knowledge, or they are unable to write like good Verilog, or like learn what they don't know the digital concept. Okay, so which is the reason that we are doing this course, like to give you a crash course to the whole thing, so you can become employed, right? And not only that, so you can get a lot of dollar-pegged jobs, okay, foreign jobs. So remote jobs which you can do from home. So for an example, I worked like that. So I joined in 2019. Yes, so no, in 2020 December. So just after COVID, during COVID time. So when I joined, like my initial salary was like what around, I was getting about 400,000 or to 400 to 500,000 rupees. So I was getting from a Canadian company. Okay. So, and that was like, so that way, like it's a remote job from here, and it's extremely valuable when you move out or like when you join other companies in Sri Lanka. So that way, like that experience is very valuable. You have good knowledge in C programming, not familiar with OOP, should be need to know these things. So, yes. So, good knowledge in electronics. Sorry, in C programming. Okay. So you don't need to know OOP concepts at all. Okay. So because like in generally in design, OOP concepts are used for like on verification side, not on design side. So if you are like unless like the people who go into full-time verification, like they learn UVM and like you use OOP a lot. But in this course, we'll be teaching you OOP, okay? Because like SystemVerilog on verification side is OOP language. So we will teaching you how to make classes and like stuff for OOP. So you don't need to know it. We will teach you whatever you want to know. So if you have C programming, then you are well suited for this course. So should we have good knowledge in electronics to continue this course? Not really. So for an example, like, so we have met with some even analog designers, so who have not done actual like PCB electronics work. Okay, not very confident in PCB electronics work. So the thing is like, so in today's world, so everything is very like you have a lot of abstractions, right? So that way, like the digital designers, they are not like, they may not be very good with analog. You need to know the concepts, of course. Okay. But, and whatever concepts you need to know for this course, we'll be teaching you. Okay. At that point, wherever necessary, we will be introducing to those concepts. And later on, you can go on and learn further. So that way, like you don't need to have like a very good knowledge in electronics to do the course. Yeah. And how can we get the Word document which includes account details and the Google form? Okay, so it should be there in your email, which we sent everybody. And I have put a link in the chat as well. So let me put that again. Yeah. So you're a computer science student from first year, first semester, CS student can do CPA design field without much knowledge in electrical or electronic. Of course you can. So yes. So to join CPU design field, you have like mainly computer architecture, like that's a big area. And at the same time, you need to have a knowledge of the digital circuits, right? Because whenever you learn the CPU design stuff, say very advanced stuff like later on you might learn branch predictors and everything. So the biggest problem is how to put that in hardware. Okay. So you can't think of like a very complex algorithm because you can't put those things in hardware. Okay. So through this course, that's why we decided to do this course first. Okay. Not computer architecture, because through this course, you will learn how to build hardware. Okay. You will get hands-on experience. You will get a feel for it. And through that, you know, like what can be put in hardware and how hard it is. Okay. So based on that, later on, when you design the CPU, you know, like what kind of decisions to make, right? So next one, when are we planning to do course 2, building this processor? So we will be planning this after a couple of months. So still we haven't like fixed a date for that. And once we do, like we will send you an email as well as a message in the group. So if you have already enrolled for this, then you'll be ready for that. Yes. So let's look at any. So Kithmin has answered like a lot of questions over here. Excellent. So there's a question: can we make a career change through this course? So of course you can. So one thing I see in this field is like a lot of people come from different areas. So even you saw like Theo is from physics, right? So like he's a physics graduate and he moved on to this. So that way you can actually the one of the biggest problems in this course is in this field area is it is generally it's a different way of thinking, right? So for an example, if you are a software engineer, the way you think to write software and the way you think to write hardware are completely different. Okay, so that is one issue. Second issue is like familiarity with the tools. Okay, so these Synopsys tools and everything, they are pretty rare. And even university, you have it for only a limited time, right? So because of that, people don't get access to that. So these are the two main issues. But through this course, we intend to solve them. Okay, so we'll teach you how to think like a digital engineer and we will teach you how to use these Synopsys tools. You will do it by your own hands. So that way, like, you will get enough confidence, and then like it will help you to change your career as well. And about the career, one thing I can say is like, so this field, chip design field, is quite safe in the sense, like it has been there for like 50 years, and even right now you have like a lot of innovation happening. Okay, so there is need for more people. At the same time, it is quite hard. Okay, so we have to admit it. It is not as easy as some of the other like very like flashy fields out there. So because of that, like you have high job security, right? So if you can do this thing very well, if you can write Verilog, if you can write SystemVerilog, if you can design things, if you know the flow, and if you know this very well, there are only very few people who do this in the world. So that way you will easily get jobs, and like they won't fire you easily as well. Okay, you can see the mass layoffs happening, but like I don't see any layoffs in hardware layers. Okay, so hardware designers generally don't get laid off that way. So it's a pretty safe field to go into as well, and it pays a lot. So if you have further questions, yeah. All right, so there's a question about ML. So will it help you in the career to continue ML side with this? Okay, so now ML is everywhere. So people are using MLs in machine learning all the places. So in my personal experience, I have worked like around 4 or 5 years now in the area of building chips for ML. Okay, so to accelerate MLs, and that is a really hot area right now because machine learning takes a lot of computation. Okay, so you have like so much computation and you need to do it very fast and efficient. So now all the companies are designing their own things, okay, own designs. So because of this, like there's a high demand for people who know both ML and basic design. Okay, so like in my CV and like when I interviewed for Qualcomm as well, so like they were pretty like happy with the fact that I know the both whole spectrum. So that way, like you can once you learn this, you can design chips for like to accelerate ML one, or else you can use ML to design chips also. Okay, so you have like two way. So you can either build like machine learning algorithms and neural networks for chip design, which is also a big field. So just like Mr. Farazy mentioned, you have like Synopsys and all these big companies are using AI in their software, okay, to accelerate chip design. So Google came up with something. So I think one of the biggest problems is floor planning, where to put these things in the chip. So that is done by, it takes a lot of time by hand. So now they are like trying to do that with AI. So if you've done this part and that part, maybe you can combine these two. And through this, you can easily get some PhD opportunities, or you can easily get placed in companies if you tell that you know both. That's an advantage. The next one, with ChatGPT also get automated without human interaction. Okay, that's a really good question. In the sense, I'm pretty sure this is one of the last field that will get replaced by ChatGPT. Okay, so because like we have seen that you have GitHub Copilot and you have some AI software which helps you write web development code, right? So you can tell what you want and it gives you. And in ChatGPT, you can see that a lot of people are trying different things. You can even write an academic paper, right? Introductions and everything with ChatGPT. But then I tried to make some modules, okay, some hardware modules. And what I got was like completely wrong. Okay, so I wanted to make an asynchronous FIFO, which is 8/3. Okay, so what it gave me was a synchronous FIFO, which is like a regular FIFO, like not a asynchronous. And it told me that it's asynchronous. Okay, so I think the issue is like you don't have a lot of hardware code online for ChatGPT to learn from. Okay, and then this feels like the chip design fields need some sort of intuition. Okay, so what we write here is not boilerplate. So generally, like we need to know like what we are doing. So which is why we are doing this course. So that way, like it's more human than the other fields, right? And so you don't have to worry about that. So then, where's to purchase the FPGA boards? So okay, that's a very good question. So if you're in Sri Lanka, it might be, I'm not sure, like it might be a bit difficult. We will give you that information on maybe the first day, or like we'll share that with you. So if you are like, you can get it from abroad. So generally you can get there are some very cheap boards. I think Arduino, FPGAs, they are like small ones. Okay. So you can always import it from abroad. So that way you can play with it yourself. So that's one of the best ways of doing it. And as a Sri Lankan student, how much we pay for this course? Okay. So if you are from ENTC, Electronics and Telecommunication Department, University of Moratuwa, then you pay, you don't have to pay at all for auditing. Okay. So because we are using ENTC resources. Okay. So in that case, you can do it without, you can do the course without the certificate. You can do it for free. Okay. But if you are a Sri Lankan university student, not from ENTC, from other departments or other universities, then the course fee is 5,000 rupees, okay, for the whole course, okay, right. So please note that the deadline is in like within 3 days, so to pay. So like please make your payments as soon as possible for the enrollment.
Yeah, quickly add to that, Abba, it's actually on 15th of February. So yeah, we've done other courses. I mean, not SystemVerilog, we've done some other courses. And when we were doing that, there were several requests from people. Can you give some more time? We'll try to accommodate those as much as possible. But it's much easier if all of you can stick to the deadlines. So that way we can, arrange all the logistics very smoothly. So I think there's a question, do fresh graduate from SLUD who hasn't found a job yet has to pay full payment? Well, there can be corner cases that does not include in the options that we talked about. You can write to us and then we'll see what we can do in those cases on a case-by-case basis. Okay, guys, do we have any other questions on Slido or are we done? I don't see anything else on Slido. Okay.
Yes, it seems like we are done. Yeah.
Right. So I hope that gave you a good understanding about the domain that we are getting into and also what you can expect from the course. We, I think, got about 175 people joining the session today. That's much more than what we expected. And we hope to see most of you from day 2 onwards as well. So a huge thank goes to all our speakers today, the keynote speakers and everybody else who joined in on a Saturday evening. It's great to see your enthusiasm. So hope we can contribute to the domain of processor design through the initiatives that we are taking here. So we look forward to seeing you on day 2. Please go through the website. Make sure you don't miss any of the instructions. Read them carefully. The instructions are there for a reason. So make sure you don't miss anything and meet the deadline so that we can smoothly organize this and we can send all the details before day number 2, that is next Saturday. So we hope to see the numbers there as well. We look forward to seeing you on day number 2. Thanks again. Have a good evening.